Okay, we will be starting our today's class. We have our marathon session today, so we will be completing a major chunk of our syllabus today. I want you guys to cooperate with me whenever I tell you that if you have any confusion, you either have to give a thumbs down or a thumbs up. Okay, whosoever is having any confusion, at the end of the slide, I will take everybody's confusion and we will be solving the doubts. Okay, so do not get scared. Feel free to ask me whatever confusion you have, whatever doubt you have in any slide. At the end of the slide, let's say this is our particular slide, I will be completing this and I'll say that this slide is complete. So anybody having any confusion. So if you do not have any confusion, no need to do any thumbs up or thumbs down. Okay, if you have any confusion, you can either tell me in the chat box or just give a thumbs down and I'll ask you. Okay, be a little bit attentive and be cooperative because this is your major chunk of the syllabus and this is the high weightage topics only. So it is very important for your exam point of view that you understand these topics pretty well. Okay, am I clear? Also, this is going to be a lengthy session, so do not worry. I will be giving you breaks in between. Okay, so whenever you feel tired, you can just tell me. We can just quickly have a 5 or 2 minutes break and then we can continue the session. Okay, I will be starting in just 2 minutes. Just a second. Okay, so our first chapter will be the D and F block elements. Okay, we have already studied about what our periodic table looks like, right? We have different kind of classifications in our periodic table. We have S block, we have P block, we have D and F block, and all the elements that are classified in these blocks, they have certain linking to each other. Now, what do I mean by linking? They have certain abilities or they have certain characteristics which are common to all of the members in a particular group. Okay, our periodic table is divided into groups and periods, right? So every element that is placed inside a group is having similar characteristics or similar abilities or physical and chemical properties as compared to the other members present in that group. Okay, this is a basic classification. So in D and F block, we know what our electronic configuration, the general electronic configuration of D block is. It's N-1, D 1 to 10, NS 1 or 2. Now, what is this N-1? What is D? What is S? See, when we talk about N-1, so the N here, it is the shell number actually. Okay, so let's say that our electron is present in the second shell. So it would be 1D because N-1, 2 minus 1 is 1. So it would be 1D, or how many electrons are present. Accordingly, we will fill the D subscript. Okay, so let's say in the D orbital, we have 5 electrons. So we will write it like D5. Okay, this is how we write the subscript. Subscript will contain the number of electrons that are present in that particular orbital. Okay, so this is our general electronic configuration of D block. We will be moving forward and going in detail of the D block. If you have any confusion, you can tell me. Now is the now it's getting started, the actual topic. Okay, so first we have the position in periodic table and the electronic configuration. Just a second. Okay, so what belongs to D block and what belongs to F block and who is truly a transition metal? Now, what is transition metal? We will be coming back to that. First, we will understand that where the D block is placed and what are its characteristics, what are the configurations and everything. Okay, so these are the elements, the D block elements I'm talking about. These are the elements which have the electrons entering the D orbital. Okay, the last electron that is present in the valence shell that will enter the D block, sorry, the D orbital of the atom. Okay, so we studied the general electronic configuration. So what is here? The S block, the D block is from groups 3 to 12, and then we have the P block. So you know our periodic table looks something like this. right? A periodic table looks something like this. This is the S block, this is the P block, this is the this is the F block, and this here is the D block, right? So our periodic table D block is situated just in the middle, and D block elements are also called as the transition metals. So the partially filled d or f orbitals are origin of their special behavior. Now, because of where they are placed in the periodic table, gives a lot of characteristics about them. So they are mostly found in the middle of the periodic table, whether it is the F block or it is the D block. F block is here in the very bottom of the periodic table, and D block is in the middle. So if we talk about the chromium, which is having the 3d5 and 4s1 configuration, and copper as 3d10 and 4s1, you can see that the d orbital is half filled and the s orbital is also half filled in case of chromium. Now, what do I mean by half filled? See, so we were understanding of about chromium and copper. So in case of chromium, see, our d block is having this is our d orbital, okay? It can accommodate 10 electrons. Now, what is happening in case of chromium? Only 5 orbitals are having electron present in it. Now, what about the rest of the 5? We could have done pairing in the 4s orbital also. The s orbital is also having only 1 electron. But according to the Aufbau's principle, we could have done pairing in the s orbital and then having only 4 electrons in the d orbital. But why are we keeping the s orbital and also the d orbital half filled? This is because the half-filled orbitals are very much stable as compared to fully filled orbitals. Okay, so this is the very repeatedly asked question in this D block. What is that? That why is chromium and copper having an exceptional electronic configuration? So what is the answer to this exceptional electronic configuration? They are having half-filled orbitals. Why? Because half-filled orbitals are usually more stable as compared to the fully filled orbitals. Okay, so this is why chromium and copper in D block are having exceptional electronic configuration. Then, when ions form, Ns electrons are removed before N-1 d electrons. So, whenever electron is removed from any d transition element, so it is not directly moved from the d orbital, it is first removed from the s orbital. So, let's say if this is the chromium here, and I have to just remove 1 electron. So, I will not remove the electron from the d orbital. What I will do, I will remove the electron from 4s1. So this orbital will remain empty because I removed the 1 electron from here, and thus the electrons are moved from the ns orbitals and not the d orbital. Then the 3D row is most important teaching model for trend analysis. Now what is the 3D row and 4D row? We will be understanding that further. Now if we talk about the F block elements, they are also the same. They are also called as, they are having two different categories. One is actinides and the second one is lanthanides, right? We will be studying them as well. So they have two blocks, which is the 4F, okay, and then we have the 5F block. Okay, so if we talk about the key comparison here, the D block element is having variable D occupancy, which means the variable D occupancy, that many elements can accommodate different kind of characteristics based upon like color, magnetism, catalysis. Many of the D transition elements are used as catalyst. Now, what are catalysts? They are the reagents or the reactants which are put in the reaction to reduce the time of the reaction. What does it mean? That means it makes the reaction move faster so that it takes or requires less time to complete or accomplish. Now, based on this variable D occupancy, the different kind of characteristics are color, magnetism, catalyst, and there are variable oxidation states as well. So for F block, we have 4F and 5F filling. So whenever we are filling electrons in F block, we are either filling them in 4F block or 5F. Okay, so there are two types of elements that are present, which are called as lanthanides and lights. I'm gonna please make the page full screen. Just a second, I'll try that. Okay, what happened, Satya? Why are you doing the thumbs down? Is there any doubt? Okay, guys, I'm a little bit sick today, so I would really appreciate your cooperation with me. Also, my camera is a little bit broken, but I will be fixing it. So please bear with me today, okay? Thank you so much. So we studied the first slide. We were on the second slide. Okay, just a second. Let me change the color. Okay. So we were studying about the placement of D block elements and what are the characteristics of F block element. So if we talk about the F block elements, we have two types of fillings. So we can either fill in a 4F orbital or we can fill in 5F orbital, right? So 4F orbitals are called as the lanthanides and 5F are called as the actinides. Okay, we will be studying them further. Then why transition metals are special? So transition elements are special because they have different characteristics. They can be used as catalysts. They can be used as different types of in different types of reactions. They have variable oxidation states. They can form numerous types of colors. They are used in bead test. They are used in color test, and they are used in various organic chemistry tests. Okay, there is Lucas test. There is reagents. We will be studying them further in the when we will start the organic chemistry portion. So D block elements are the most special as in the periodic table as compared to the S block or the P block elements. D block elements are very versatile because they are used in various kind of reactions as different types of elements. If we talk about the S block elements, the alkaline earth or alkaline metals, so they are also used in various reactions, but they do not give any colors, different kind of colors. They do not have partially filled orbitals, and they are not used in catalyst as in any reactions. So this is what makes the D block elements pretty much variable as compared to the other elements or other blocks that are present in the periodic table. So if we talk about P block elements, they are called as transition metals, while as if we talk about F orbital or the F block, they are called as inner transition elements. Okay, you need to remember this. D block is called as transition, while as F block is called as the inner transition elements. So their partially filled d orbitals gives them unique properties. So because their orbitals are not completely filled and there is no pairing of electrons and they are half filled, this half filling of electrons in their orbitals is what gives them special abilities to act in different ways. Okay. So first we have the variable oxidation states. So what is oxidation state? Oxidation state is basically the number of electrons that are gained or lost by an atom. Okay. So variable oxidation state here means the both Ns and D electrons are participating in the bonding. So let's say this is our S orbital and this is my d orbital. Okay, so when I'm talking about the transition elements, both the electrons that are present here in the ns and the n-1d, both of the electrons are taking part in the bonding. So therefore what is happening, they are having variable oxidation states. So there is a number of permutations and combinations that you can make in case of oxidation state for transition elements. This is what we call as the variable oxidation state. I'll just quickly give an example. Like if we take iron, it is having +2 oxidation state, and it is also having +3 oxidation state. So do you see what is happening here? Iron is one element and it is having two oxidation states. That means it is belonging to the D block element, right? It is a D block, it is a transition element. And what is happening? It is not confined to only one um, the oxidation state, but it is having numerous or more than one oxidation state, which makes it variable. If we take another example of manganese, we know manganese exists from +2 to +7. So do you see here what is happening? +2 से लेके +7 तक everything is getting in the manganese की oxidation state. So manganese will have +2, +3, +4 up to +7 oxidation state. So again, manganese is also not confined to +2 or +7 only, but it has a series of oxidation state. So I hope our variable oxidation state is clear. Then we have the colored ions. So what do we mean by colored compounds? The transition metal absorbs the visible light due to DD transition. Now what is DD transition? Basically, you know what is transition? When the electron gets excited and moves to a higher state, right? That is what happens when a d orbital gets excited and it moves here and there. So we have DD transition, and because of these DD transitions we get colored ions. So what happens? The electrons that are present in the d orbital, they absorb a little bit of visible light, and then a certain color is thrown out. Okay, so that is the color which is seen by us in different kind of reactions. Let's take an example. If I take copper 2 positive, copper 2 positive is blue in color. Okay, if I take iron 2 positive, iron 2 positive is green in color. Okay, so why are we considering this color? Because when we are doing certain kind of reactions, we have to be very careful as compared, we have to be very careful working with these compounds, because on the basis of color you can judge whether your reaction is working or not, are you getting the desired compound or not. That is why these compounds are special, because they are able to show colors in different kind of compounds. Okay, then the third thing, this is not visible here. Just a second. We studied the colored compound, and then we have the complex formation. Okay, let's move to this. Now, what is a complex? So transition metals easily form complexes. See, if I am saying that, let's say NaOH, this is my compound. Okay, this is my one simple compound. If I am making a complex, let's say Na is getting mixed with some sort of more than 7 water molecules, and it is having some more Cl2 positive, and this whole is having some charge negative. So what is this? This is a compound? No, this is not a compound, this is a complex. A complex is where different kind of compounds are mixing together and coming out as a whole. Okay, so this NaOH, this is just having sodium, oxygen and hydrogen. But how many elements do we see here? We see chlorine, we see water. Water is itself a compound, right? It has 2 hydrogens, oxygens, and we have 7 molecules of water. And then we also have sodium. So this kind of compound is not called a compound, it is a complex, where different kind of elements are clumped together to form a one compound. Okay, so this is what we call as the complex. So these DD transition metals, or the transition metals itself, they are known for complex formation because of their small size, their high charge and vacant orbitals. Because उनके जो orbitals होते हैं, they are half filled. So because of the half filling, there is vacant space for reagents to act, and therefore they can make different kind of compounds. Let's take another example. See, this is a compound. We have Cu in it, we have ammonia, NH3, we have 4 molecules of ammonia, and then we have a positive 3 charge. So this is a example of compound which are made by the DD transition or the transition metals. Then we have the catalysis and reactivity. So catalytic activity of these transition metals, they act as catalysts because they show variable oxidation state, which we studied here, that why are they having variable oxidation state, and then they form intermediate complexes. Now you must be familiar with what an intermediate is. See, if we have a reactant and it gets converted to products, now this is a simple reaction. Now, if in case of reactants, at some point in time, at some point in the reaction, we are getting a compound that does not stay there for a pretty long time, and this compound gets converted to the products. This compound right here is called our intermediate. Intermediates are very short-lived and they do not remain in the reaction for a very long time. They, within a blink of the eye, they get transferred to the products or converted to the products. So the D elements show catalytic behavior because they are able to form these intermediate. They are able to form the complex intermediates. Okay. For example, we have iron in Haber's process. In your 11th or 12th, basically, you might have understood what is Haber's process, in which we make the ammonia, right? We make a cycle of ammonia. So we are using uh, iron in Haber's process. This is also a this is an example of catalytic behavior. And then the last thing here, I guess this is magnetism. From the magnetism of this D block elements, we are having a very important formula. Most of the questions in your IMUCET get asked because of those, on directly on the basis of that formula. Okay, so basically unpaired electrons are what is causing magnetism or paramagnetism here. See, if we are taking a complete paired electron and an unpaired, so this is diamagnetic and this is paramagnetic. Paramagnetic means unpaired electrons. Okay, so magnetic formula for these uh, D block elements would be, we denote it as mu, and then we have the square root of n into n plus 2 bn. Okay, this is the unit of this. So whenever I say, let's say I give you a compound and I tell you that can calculate the magnetism of this particular compound, so you will apply this formula uh, in order to calculate the magnetism. Okay, this is Bohr's magnetism here. So n is the number of unpaired electrons. So let's say, let me quickly take an example. Let's say my total number of unpaired, let me erase this here. Let's say my total number of unpaired electrons is 2. Okay, so I have to calculate magnetism mu. So what will I do? I will take the under root and then I will put 2 here and then 2 plus 2, which comes out to be 2 plus, sorry, this is 4 here. So it is 2 into 4, 4 to our 8. So this is under root 8, or you can write it as 2 under root 3 is our final answer, or you can also calculate it for the decimal answer also. I just gave you a pretty decent example of how to calculate the Bohr's magnetism. Okay, so let's say you are having 5 electrons in d orbital. That means you are having 5 unpaired electrons, right? 1, 2, 3, 4, and 5. So what will be the mu in case of when you have 5 unpaired electrons? Can you just quickly do it? Try the 5 unpaired electrons and then I will give you one more example. Just try it once. We have 5 unpaired electrons. You just have to put 5 in this formula. Wherever you have n, put 5 there and then just calculate. Okay, just quickly tell me what is the answer. Okay, see, I will be giving you one more example here. See, let me just remove this thing here. I told you that we have D5. That means it has 5 unpaired electrons, right? So what do we have to do? We have the magnetic moment mu as under root n into n plus 2, right? So we just have to put 5 wherever we have n. So we will put 5 into 5 plus 2. So this is 5 into 7, and 5 into 7 we have 35. So our magnetic moment mu is coming out as root 35, or you can also approximately write it as 5.2. Okay. Okay. Satya Vijay, you are correct. Samson, you are also correct. Root 35 is the correct answer. Okay. Okay. So root 35 is the correct answer. Now, the maximum oxidation state diversity appears near the middle. Mn reaches positive 7. So, uh, Mn will have the most number of variable oxidation state, which is varying from +2 to +7. Okay. Then we have color and magnetism depend on the d electron arrangement. However, we have the different arrangements of d electrons. It will affect the color and the magnetism. The number of unpaired electrons you see. When we have 2 unpaired electrons, we got root 8. But when we have 5, sorry, when we have 5 unpaired electrons, we got root 35 as our answer. So the magnetic moment will also depend on the number of d electron arrangement. Okay, then they have small size, high charge, and orbitals, easily complex formation. So because of their small size, because of the high charge and variable oxidation state, they are easily forming complexes. Okay, I told you what are complexes, I told you what is compound formation, I told you orbitals. If anybody is having any doubt in this slide, tell me, otherwise we are moving forward. Okay, let's move forward then. Then we have important trends in the first row transition series. Then first we have the atomic size. So across 3D series, it is very slight. So atomic size across a period, atomic size decreases slightly. Okay, so if we are saying across a period, groups are like this and periods are like this, right? So across a period, that means going from here to here, what will happen? Your atomic size will decrease. Okay, it will, the element that is present here will have a larger size as compared to the element that is present here. It will have a smaller size. So across a period, the elements are doing what? They are decreasing in size. This is happening because the nuclear charge is increasing. The ability of the nucleus to pull the electrons towards itself is increasing, and therefore the size is decreasing. Okay, so this is majorly seen in lanthanides. Then we have the ionization enthalpy. Generally increases slightly but irregularly. So what is happening here? So ionization enthalpy, we know what is ionization enthalpy. It is the energy required to remove the last electron present in the valence shell. So if this is our atom and this is the electron present here, so the amount of energy that will be required by me to pull this electron out of the element is what our ionization enthalpy is. How much energy will be needed in order to take out the electron from the atom is our ionization enthalpy. So across the group, what is happening here? It is slightly increasing, but it is very irregular. That means every element is not cooperating with the trend. Okay, so this is happening because of the half-filled d orbitals. We studied what are half-filled d orbitals, right? And the fully filled d10 orbitals. Now d5 orbitals are partially filled, while as d10 orbitals are fully filled. Now why does ionization enthalpy show irregularities? Because of these two characteristics. Fully filled d orbitals or the partially filled d orbitals. Okay. Then we have the enthalpy of atomization. Okay, very high due to strong metallic bonds. Now, what are metallic bonds? Metallic bonds are existing between metals, and therefore, the sharing of electron when happens between two metals, we say that it is a metallic bond. So, what happens in case of atomization? The very due to very high metallic bonding, the middle elements show maximum values. So atomization is basically the high values of the middle elements. Okay, so this is happening because of the metallic bonding. When two metals are having bond in between of them, there is atomization. Okay, and this atomization values is maximum for the middle elements. Now what are middle elements? It is the d block elements, right? Then we have the density. You know what density is, right? I don't need to explain what density is. So generally density increases across a series. Now what are series is? We have different kind of, we have carbon series, we have different series like lanthanide series, actinide series, right? So it generally increases in a series because of the mass differences. Now the size is changing, right? The nuclear charge is also changing, and therefore the density of the atoms is also changing. So what happens across a series? It generally increases. So if we are taking, let's say, lanthanide series, let's say this is our lanthanide series, and if we go from this point to this point, what will happen? The density here, which is usually written as rho, it will be the maximum here, sorry, it will be the lowest here, and then moving on to here, it will be the maximum here, because it across a period or across a series, it is increasing. So here it will be very low, but here on this point it would be higher. Okay, so this is about density. Then we have a very important concept which is called as the lanthanide contraction. So what is happening in lanthanide contraction? It is very important topic. There is a gradual decrease in size of lanthanoids from La3 plus to Lu3 plus. See, let me just quickly erase this portion. So there is a decrease in size from La3 plus to Lu3 plus. You can write plus 3, 3 plus, whatsoever, it means the same. Okay, so what is the reason? This is why 4D and 5D congeners often show very similar chemistry. Now 4 of electrons shield very poorly. So what is shielding? Shielding is basically the ability of the inner electrons to protect the outer electrons from moving out. See, this is my electron here. So what will these inner electrons do? They will try to shield, they will try to protect the outer electrons from moving out of the atom. So this is called as shielding. But 4D electrons are very poor in shielding. They are not able to protect the outer electrons, and therefore ionization energy is very low because the bonding between these electrons is very low. So what is happening? Because of the poor shielding, this lanthanide contraction is happening. The size is decreasing. Why is size decreasing? Because when these inner electrons are not able to protect these electrons from moving out, they will eventually move out. And what will happen? This shell will cancel here. So we will only have two shells. So what happened? Let's say here is size was 2, and now here size is 1. So size is decreasing. Why is it decreasing? Because of poor shielding. Okay, so poor shielding results into the lanthanide contraction. This is a very important concept in your exam point of view. Very much questions get asked on the lanthanide contractions. And what happens as a result, the 4D and 5D elements become nearly equal in size. This is what we call as the lanthanide contraction. Because of the poor shielding of 4D electrons, what is happening? There is a gradual decrease in the size from La3 plus to Lu3 plus. And what happens as a result? The 4D and 5D electrons become nearly equal in size. Like you can see, the zirconium and hafnium here, they are almost equal to size. See, 160 picometer and 159. Okay, ma'am, is it 4F? No, it is 4D and 5D elements, Bacha. Okay, so zirconium and hafnium are nearly equal. This is happening in the F block. It is happening in the lanthanide contraction is happening in F block, but the result is seen in the D block because 4D and 5D elements are present in the D block. No, So as a result, what is happening? There is a contraction. They are almost becoming equal in size. But what is happening? What do we actually call as lanthanide contraction is the gradual decrease in size of the lanthanides from La3 plus to Lu3 plus. So what is an effect? See, let's say let me make you explain like this. For example, there is a nuclear war going on. Okay, so what is happening? Let's say some country is doing nuclear war on some other country. Now there are after effects after the war. There is poverty, there is unemployment, there are different kind of criterias which are resulting because of the war. Now this is also, let's say there is a war going on between the lanthanides. Okay, so they are getting decreased in size. Now what are the after effects of these war? As compared to the poverty and unemployment, this is not the case here. So what is the after effect? It is making the 4d and 5d electrons similar in size. This is the after effect of lanthanide contraction. Is this clear? Okay, so example, I told you zirconium and hafnium are the example. Because of the lanthanide contraction, they are almost equal in size. Okay, we will be doing one more slide and then we will quickly take a 5-minute break. Okay, we are doing this slide again. So next we have oxidation state and redox behavior. Now you might have understood what are redox reactions, where both oxidation and reduction are happening simultaneously hand in hand. Okay, so oxidation state, highest oxidation state rises till manganese and then decreases. So manganese, I told you it will have +2 to +7, right? So manganese is having the highest oxidation, variable oxidation state. First, it will increase till manganese. See, you can see +3, +4, 5, and 6. So up to manganese, it is increasing. But then from the further from the manganese, it is decreasing. You can see 6, 4, 3, 2, 2. Okay, so up to manganese, first the oxidation state of the elements will increase and then it will gradually decrease. Okay, we understood what is oxidation state and how they are showing different variable oxidation states. So up to manganese, the maximum oxidation state roughly equals Ns plus N minus 1D. This is the basic formula, okay, to calculate the number of variable oxidation state. So we know you just have to remember what is the uh, the oxidation state of manganese. And now I have repeated it so many times that you will have been remembering this thing. It is +2 to +7. You just have to remember it for the manganese, and the rest you know. On the left side it is it is increasing, and on the right side it is decreasing. Okay. Sorry. Then, after manganese, higher oxidation state drops in stability. That is Fe2 or Fe3, copper, sorry, cobalt 2 and 3, nickel 2, copper 1 and 2, zinc will dominate. That means they are having stable oxidation states. If I take Fe positive and Fe2 positive, this is not a dominating variable oxidation state, but Fe2 plus is dominating. Why? Because it is more stable in 2 plus or 3 plus. So Fe plus is not as that stable as compared to the 2 and +3. So then we have cobalt 2 and 3, nickel 2, copper 1 and 2, zinc 2. These will dominate. Okay, they are more stable in these oxidation states. They can exist in the previous, like iron can exist also in +1 state, but it is better, like iron wants to be in +2 or +3 oxidation state. Okay, then we have low oxidation states are stabilized by pi acceptor ligands such as CO in NiCO4 and FeCO5. So the low oxidation states are stabilized because the low oxidation state will not act in much of the reaction. So how they are stable? They are stable by pi acceptor ligands. The ligands are the reagents which donate some electrons. Okay, so pi acceptor or sigma donator ligand will help in stabilization of oxidation states. Then we have the redox points or the redox anchors. So chromium 2 positive is reducing because chromium 3 positive D3 is more stable. So what will happen in case of chromium 2 positive? It is reducing. That means if you put it in any kind of a reaction, it will make a reduction to the other compounds. It will remove the hydrogen. Okay. So what is oxidation? Oxidation is adding of oxygen, and what is reduction? Removal of hydrogen is reduction. So whenever copper 2 positive is present anywhere, it will act as a reducing agent. Okay. Then we have manganese 3 plus. It is oxidizing. That means it will add oxygen. Okay, because Mn2 plus is exceptionally stable. Okay, if we talk about the manganese, ma'am, but it states that after manganese, higher the oxidation state, the stability drops. So if Fe2 plus is stable, then Fe3 plus. Just a second. Ma'am, it states that after manganese, higher oxidation state, stability drops. So it is Fe2 plus is stable than Fe3 plus. Yes, beta, it is stable as compare see, you have up to manganese, the maximum oxidation state roughly equals, okay? And then we know that after the manganese, it will gradually decrease. But then we know Fe2 plus and Fe3 plus, both are stable. But it is better to look upon the stability criteria as compared to the reaction. There are some reactions in which Fe2 plus will be more stable as compared to Fe3 plus, but there are also few examples of some reactions where Fe3 plus is considered more stable as compared to Fe2 plus. So basically the all this thing which is here, this is a variable oxidation state, and you just have to look upon which criteria is more stable as within the reaction. So whatever amount of reaction you have, whichever reaction you have to see according to that. So which iron, either 2 plus or 3 plus, will be more stable. So it depends basically on the reaction. We cannot generalize that Fe2 plus is more stable as compared to Fe3 plus, but you have to look upon the reactions. Okay. So both Fe2 and 3 both are stable, but you have to look according to the reactions, that which is the most stable. Okay, 3 plus can also be stable, 2 plus can also be stable, but there are the conditions where the iron will act more relevant. Okay, so this is how we do it. Then we have the, where was I? Okay, I was here. So Cu does not liberate H2 from non-oxidizing agents. So this is basically the E standard of copper, and we know that copper does not liberate H2 from non-oxidizing agent. This is basically a property of copper. So oxidizing power, if we take of various oxides of the D block elements, this is the what do we say, the series of oxidizing power. Okay, you do not need to remember this. We will be doing questions, and that will make you practice a lot of concepts. Okay, you do not need to memorize anything. There are few students who remember it most because they memorize things. It is better if you want to memorize. Like still, if you do not, if, like many of the students have difficulty in memorizing chemistry. So I'm not saying that you need to memorize things. Just understand the concept, and then you can do the questions. It's better if you are having the concept than memorizing things without the concept. Okay. Almost 1 hour is done of our class. We will quickly take a 5-minute break. Then we will continue with our sixth slide. Okay, then we have color and magnetism next. The next thing we have is color and magnetism. Okay, so what we know about color, I told you that because of the DV transition, what is happening, the D elements are able to change colors, right? They give different kind of colors in different kind of reactions, right? So what is happening here? The color arises when electron is promoted from a lower D level to a higher D level, and the absorbed light lies in the visible region. Now, what is happening here? The color is arising because the transition is happening. Now, transition happens because of what? It happens because the electron present in the lower level moves to a higher level. So, the electron present in the lower D level, when it moves to a higher D level, it releases some light. And if that light lies in the visible region, then we can see any particular kind of color. So D0 and D10 ions are usually colorless. So if any element is having either 0D or D10, these kind of compounds are usually colorless. Okay. Typically aqueous colors are like uh, titanium 3 positive is purple, Fe2 positive is green, and Cu2 positive is blue. You do not need to remember each and every ion ka color. So you just need to remember few which are the most expected or highly repeated questions. Okay, you also know that chromate is yellow in color, dichromate is orange in color, right? So the color, why is the color arising? It is arising because of the DD transition. Now, what is DD transition? It is when the D electron from a lower level gets converted to a higher level or moves from lower level to a higher level, and therefore energy is released and absorbed. And if the absorbed light lies in the visible region, then we can see a particular color associated with that wavelength. Okay. Then we also studied what is paramagnetism and what is diamagnetism, right? I told you unpaired electrons are called as paramagnetism. They are attracted by magnetic field, and diamagnetism means there is no unpaired electron present in the compound, and that means they are having weak repulsion. Okay. I also told you this formula. We also learned how to calculate magnetic moment, right? So more unpaired electrons, the larger the magnetic moment. We saw in case of 5 unpaired electrons, we got root 35, and in case of 2 unpaired electrons, we got root 8. So the greater the number of unpaired electrons, the greater will be your magnetic moment. Okay. Then we have example of Mn2 plus is D5. So N is equal to 5 or approximately 5.92 BM. It is actually root 5. So it is approximately 5.92 Bohr's magnetron. Okay. Moving forward, we have complexes, catalysts, and interstitial compounds and alloys. So what is having one family of metals, many practical consequences. So complex formation, the small size and high charge and available oxidation states and different oxidation states and the free orbitals is what gives rise to the complexes. So the small ionic size and vacant orbitals, it is orbital here, vacant orbitals gives rise to complexes. So complexes are common because metal ions are small. They are charged and have orbitals available for bond formation, and low oxidation states are often stabilized by pi acceptor ligands such as CO. We also saw an example in the previous slides of pi acceptor ligands. Then we have, I told you an example of iron in Haber's process as catalyst, right? Then we have interstitial compounds. They are the metal lattices, which means there is a combination in a certain kind of shape, which we call as the lattice. You might have studied different kind of lattices in solid state chapter, right? There is the shape of diamond, there is the shape of graphite, there is BCC, and different kind of lattices like that. So interstitial compounds are the metals that are present in some sort of lattices. And then there is alloy formation. So you know what is alloy? Like bronze is an example of alloy, which is made up of two metals, the combination of two metals, right? So the alloy formation is also happening because of the transition elements, because they form metallic radii are very small and they easily form complexes. Then we have the important compound, that is potassium dichromate. It is very important as compared, for the exam point of view. So potassium dichromate is an orange crystalline solid. Okay, we know its color is what? Kabhi what happens? It's directly the question gets asked that what is the color of the potassium dichromate? So you know it is orange in color. Okay, it depends on the pH. So it is a strong oxidizing agent in acidic medium, that whenever there is some acid present in the medium, it will act as an oxidizing agent. That is, it will add oxygen to the other compounds. So potassium dichromate, the fusion with Na2CO3 in presence of air and acidification, then when it is treated with KCl, we get K2Cr2O7. Okay. So if you just get asked a question about how potassium dichromate is formed, it is formed by the fusion of Na2CO3 in presence of air, and then it is acid. Then acidification is done on that. That is in presence of acid. The oxidation is done, and then it is treated with KCl, and therefore we get our compound as K2Cr2O7. So chromate is basically yellow in color, but when it is changed to dichromate with the help of this particular reaction, the color changes from yellow to orange. Okay, in many questions it will get asked to you that what is the color of chromate and what is the color of dichromate, or you will get asked like how many H plus ions did we use in the reaction. Such questions will get asked in your exams. Okay, so why does it matter? Orange crystals, they are strong oxidizing agent, especially in acidic medium. We understood that potassium dichromate is a crystalline solid. It acts as an oxidizing agent in acidic medium, and therefore the Cr2O72 minus will consist of two tetrahedra sharing one oxygen atom. If we talk about the structure of this potassium dichromate, so Cr2O7 will consist of two tetrahedrons sharing one oxygen atom. And usually in leather industry, it is used as a primary oxidant in synthesis and analysis. If there is a question asked to you like in which industry is the potassium dichromate used, so it is basically used in leather industry in the primary oxidant in synthesis. Okay, so typical oxidations of this is, you can see I2, Fe2 plus, Fe3 plus, and the oxidation from here, the reduction happens, H2 is removed and only sulfur remains. This is the uh, reaction that you need to remember in case of potassium dichromate. Okay, so basically what did we study about potassium dichromate? That it is an orange crystalline solid. It is strong acidic reaction. It is strong in case of acidic medium. It acts as a strong agent, oxidizing agent. And then chromate is yellow in color, but when we process it with KCl, it changes to dichromate, and therefore dichromate is orange in color. Okay, so the reduction example we saw the reaction of potassium dichromate. So this was our first important compound, and the next important compound is potassium permanganate, which you also call as KMNO4. Okay, so these are the two very important compounds as compare. Sorry, for your exam point of view. So dichromate was orange in color. This compound is purple in color. Okay, so how is it prepared? MnO2 is synthesized with K2MnO4, and then we get KMnO4. So what is happening here? It is a very strong oxidizing agent. Okay, that means it will add oxygen. In acidic medium, Fe2 plus, C2O4 2 minus, I minus, NO2 minus are readily oxidized. That means wherever you have acidic medium and then you put KMNO4 in a reaction and these compounds are present, so they are readily oxidized. That means they will be oxidized till there is no oxygen left. Okay, readily oxidized means they will be continuously oxidized until no oxygen is left. Okay, then we have neutral or faintly alkaline medium often gives MnO2 as a reduction product. If there is a neutral or alkaline medium, so there will be a reduction product. That means there will be hydrogen will be removed from the compound. And then permanganate titrations are not done with HCl because Cl is oxidized. So you will never see KMNO4 being used in titration reactions. Why? Because it's in HCl, the Cl is oxidized. Okay, then we also have some reduction products. That means if you put KMNO4 in any of these reactions, so you will get the main product as, if there is acidic medium, you will get Mn2 plus. If there is neutral or alkaline, so you will get a reduction product, that is MnO2. And if there is strongly alkaline, that is basic nature of the compound is there, so you will get MnO4 2 minus. Okay, so this is the reaction that you need to remember in case of potassium permanganate. Okay, then we have the snapshot of lanthanides and actinides. We studied in the previous slides what are actinides and lanthanides, right? We studied lanthanide contraction. I told you the after effects of lanthanide contraction, right? We will be studying them in a little bit detail again. So they both fill inner orbitals, but their chemistry is not equally simple. So in case of lanthanides, what is happening? 4F filling is happening. So it is from Cu to Lu, and most oxidation state, stable oxidation state is +3. So if you have 4F elements and somebody asks you like what is the most stable oxidation state of 4F orbitals, then you have to say that +3. There are other oxidation states as well. There is +4, +5, +1, but the most stable is +3. Okay. Then the study size decreases across the series. That means I already told you when we go across a series, the size decreases and the ionization enthalpy increases. Then in case of Ce4 plus, it is an oxidant, uh, and in case of Eu2 plus and YV2 plus, they are reducing because F7 and F14 are extra stable. Now we have studied the concept of half filled and partially filled and fully filled, right? So we know that F7 is also stable and F14 is also stable. So in case of these these elements, the F7 and F14 stability is the filling is more stable, and therefore they act as reducing agents. Okay, and the members resemble each other closely because their separation is different. Now I told you in the in the starting of this chapter that in our periodic table, when anything is put inside a group or a series, so they have similar characteristics with each other. That is why they are there as a company in some series or in a group, right? So let's say you have a friend group of, let's say, 7 people. So why are certain people friends for a longer period of time? Because they match their energy, right? Their vibes are matching, and therefore they are remaining as friends. Similarly, what is happening in case of groups or series, the vibes are matching of the elements, and therefore they are placed in a certain group. Okay. So 4D and 5D elements show unexpectedly. Just a second. So the consequence of contraction, I told you, unexpectedly reduced size. It is not. It is not. It is size. Okay. So because of the contraction, the 4D and 5D elements are almost similar in size. We saw the example of zirconium and hafnium there, right? Then we have the actinoids. The 5F filling from thyroid to LR are all radioactive. So all the actinoids that are present in the F block, they are all radioactive. Okay, that means they are not basically used in reactions, simple reactions, but they are used in nuclear reactions because they are very reactive or radioactive. So oxidation states are most variable from +3 to +7. That means any of the oxidation state from +3 to +7 can be seen as stable, especially in early actinoids. 5F, 6D, and 7S levels are close in energy, so bonding was more complex than in the lanthanides. Okay, so in case of 5F, 6D, and 7S, the levels are very close in energy. That is, they are having very little difference in the energy of the different levels. So therefore, the complexes that are formed by actinoids are very complex as compared to the compounds or bonding that is done in lanthanides. And then we have actinide contraction is greater because 5F shielding is poor. Now I told you how what shielding is and how does shielding happen and how the size reduces because of the shielding. And there 4D shielding was 4F shielding was very low, and here 5F shielding is very low. So lanthanides mostly +3 and smoother chemistry. That means they mostly show +3 stable oxidation state, and they have smoother chemistry as compared to the actinides, because actinides are radioactive. They are not very easy to study, and their complex formation is also very difficult, and they form their bonding is also very complex as compared to the lanthanides. Then we will do a quick revision of the chapter. So we studied what partially filled d orbital is, right? So it is variable oxidation state. We studied about color, how color is there. It is because of the dd transition. Then we studied the magnetism, where we studied this formula. You have to remember this formula because many questions will get asked in on the basis of this reaction. Okay, then we studied about complexes. We also studied that why D elements are used in catalysis. So general configuration of D block elements is 1 to 10, N is 1 to 2. Okay, then it is happening because of DD transition. The colored ions are there. Cr and copper, that is chromium and copper, will show exceptional oxidation state. Why? Because they have half filled electrons. And across 3D series, size decreases slightly, ionization energy increases slightly, and atomization stays high. Okay, then maximum oxidation state peaks near manganese +7. We also studied that manganese will range from +2 to +7, right? Then unpaired electrons will have this formula to calculate the Bohr magnetron, right? Chromium, sorry, chromate is yellow in color. When it gets changed to dichromate, it changes to orange in color. Oxidizing power is having this series. Then lanthanide contraction makes 4D equal to 5D. Important points to remember is uh, the two compounds that we studied, dichromate and permanganate, right? You need to memorize the reactions and uh, try questions based on them in order to make your practice more efficient. Then we have the topic wise questions. So we have questions in the next PDFs. We will be practicing our questions. So these are simply some questions that you can ask yourself to see if your concepts are clear. Okay, we will be doing the solving portion at the end of the session. I will be assisting you with solving part. I guess we have 40 questions, so we will be doing those questions as well. So these are basically the oral revision, or you can say your homework checks. Okay, so you have to understand and ask yourself these questions in order to revise the chapter. If you are able to answer these questions on your own, that means your concepts are very clear. But if you are not able, then you are free to look for some resources. You might have been provided with different resources from your budding mariners team, right? So you need to look for the material and revise the entire chapter. Okay, you can also ask me if you have any confusion. You can normally reach out to me and I will guide you. Okay, this is also some questions that you need to. And so basically the last two slides are your homework. This is to check whether you have understood the chapter or not. So basically your two chapters are done here, that is the D block and F block chapter is done. Okay, we will be moving next with hydrocarbons in just 5 minutes. Okay, guys, we are moving forward with our second chapter, which is the hydrocarbons. It is basically from your NCRT class 11, right? So, in this chapter, I will be explaining everything related to the hydrocarbons. Okay, so here the general focus will be upon the formulas and bonding nomenclature, preparation routes, signature reactions, Markovnikov's and anti-Markovnikov's rule, right? Conformations of ethane, aromaticity, electrophilic substitution, and then we will learn about the classification of alkanes, conformations, alkenes, alkynes, aromaticity, which is benzene and arenes, and then we will finally do the revision. Okay. So first we are having the classification of hydrocarbons. So it is an important chapter in organic chemistry, hydrocarbons, okay? So hydrocarbons are grouped by the type of carbon-carbon bonds present in them, okay? So hydrocarbons are the compounds which are mainly consisting of two things. As you can see, the name suggests Hydro means hydrogen and carbon means carbon. So basically two things, hydrogen and carbon. This makes our hydrocarbons. Okay. So these compounds are everywhere around us, whether you see it in LPG gas, you see them in petrol, diesel, CNG, plastics, wax, or cooking gas that is used in your households, right? So everywhere hydrocarbons is present in our daily life. Even the fuel in vehicles is mostly hydrocarbons, okay? Whether it is petrol, diesel, it is all hydrocarbons, okay? So basically what we studied about hydrocarbon, they are the compounds which are mainly made up of two things, hydrogen and carbon. This chapter will build from nomenclature and isomerism to preparation, properties, mechanisms, aromaticity and directive effects. The core reaction will be pattern shifts across the family, alkanes, substitutions, and then we will move on. Okay, so you have the basic classification of alkenes, which is having this formula. Alkanes will have this formula, alkenes will have this formula, and arenes are having the aromatic pi system. We will study each and every of them, these compounds, in detail, so don't worry. So basically you got the little bit idea of what hydrocarbon is, what is its classification, and what does it consist of, and where is it used in our daily life. Okay, then we have the definition and importance. So hydrocarbons are divided based on the type of bonds or carbon atoms between them. So hydrocarbons are the compounds containing only carbon and hydrogen. We understood this thing. Let me just zoom in here. So important as fuels, which is LPG, CNG, petrol, diesel. I told you, whether it is your cooking gas that you're using in your household, it is the fuel in your car, it is the diesel in your car, or the LPG that is present in your cylinders. All of them are hydrocarbons. Okay, they are used in manufacture of polymers, dyes, drugs and solvents. Now this is not the drug that is used for misuse. These are the drugs which we call as medicine. Okay, they are used to treat some disease. These are not the drugs that are misused. Okay, then we have the main classification of hydrocarbons. First, we have the saturated hydrocarbons, and the saturated hydrocarbons are called as alkanes or the cycloalkanes. Okay, these are the saturated hydrocarbons, and then we have the unsaturated hydrocarbons, which we call as alkenes and alkynes. Okay, then we have the aromatic hydrocarbons, which we call as the benzene and the other aromatic compounds or the related compounds. So this is the main classification. Okay, there are mainly three types of hydrocarbons. First is the saturated, then is the unsaturated, and then we have the aromatic. Okay, then we will learn about nomenclature, methods of preparation, physical and chemical properties, conformations of ethane, and aromaticity of electrophilic substitution. Now the main classification, first of all, we have alkenes. Okay, alkenes contain only single bonds. Okay, let's say if I have a carbon atom here, this is C bond C. Okay, and here we will have hydrogen, hydrogen. This compound here is our alkane because it is only having single bonds, only sigma bonds. Okay, so general configuration of alkenes is CnH2n plus 2. Okay, example is methane. I can show you CH4. We have ethene, C2H6. This thing which I made, this is ethene, and then we have propene, which is C3H6. Okay, these are some basic examples of alkenes. They are all saturated, that means all the bonds are single bonds or what we call as the sigma bonds. Then they show chain isomerism and conformations, and the main reaction is substitution reaction. Okay, they are called saturated hydrocarbons because the carbon has maximum hydrogens attached to it. That is why alkenes are called as the saturated hydrocarbons. Then we are moving forward to alkenes. Alkenes contain at least one double bond. Okay, they have at least one double bond, and their general configuration is CnH2n. Okay, and they show geometrical isomerism. Now, what is this? We will study this in isomerism part. Then their main reaction is electrophilic addition reaction. Okay, then we have alkynes. I did not give you examples here. The examples will be ethene or propene. You can take whatever example you like according to you. I am just giving you a simple uh, examples. Okay, these are unsaturated hydrocarbons because they are having double bond in between of them. Then we are moving to alkynes. Alkynes contain at least one triple bond. Okay, at least one. There can be multiple, but at least one should be present there. So general formula is CnH2n minus 2. They contain at least one triple bond, and the terminal alkydes show acidic character, and they undergo addition reaction. Example, ethine, propine. Okay. Then we have arenes. Arenes are the aromatic hydrocarbons. They are the benzenes and their derivatives. These contain benzene ring-like structure. Now you know what is benzene. It is a hexagon like this, right? This is our benzene. So all the arenes are benzene and its derivatives. Then we have aromatic and planar resonance stabilized. That means they are either aromatic stabilized, they are planar resonance stabilized, or anything else. And then they prefer substitution over addition. Example, benzene, toluene, right? So this is the basic classification of our entire chapter. Does anybody have any issue till now? Any doubt? Okay, quickly give me a thumbs up that everybody understood. Okay, great. Let's move forward. Then we have the alkenes. Sorry, alkanes. Now we will be understanding the preparation properties and key reactions of these alkanes. Now, first of all, what are alkanes? Alkanes are the hydrocarbons which are having only one single bond or one single covalent bond. I gave you an example of what? I gave you an example of methane. Sorry, this is not visible. I gave you an example of methane, which was CH4, right? This looks something like this. Okay, so this is only having single bonds, so therefore this is an alkane. So carbon in alkanes is sp3 hybridized. They are tetrahedral in shape, and the bond angle is 109.5. I will write these things down here. The carbon that is present in alkanes is sp3 hybridized. It is tetrahedral, and the bond angle is 109.5 degree. Okay. So hydrogenation of alkene, the preparation of how alkanes are prepared. They are prepared by hydrogenation of alkenes or alkynes, the reduction of alkyl halides, Woods reaction, decarboxylation with soda lime, and Colby electrolysis. Now, whatever the reactions are necessary for your exam point of view, we will be studying them further. Then we have physical properties. All the alkanes are almost non-polar. That means there is no unequal distribution of charge. Okay, you know what is polar and what is non-polar. Let's say I take an example of HCl, right? I'm taking an example of HCl. Cl is electronegative, so it will have a negative delta charge on it, and hydrogen is having a positive charge on it because it is less electronegative. So electron cloud will be shifted towards chlorine. And this is what we call as unequal distribution of charge, and this usually happens in polar molecules. But here alkanes are usually non-polar. That means there is no unequal distribution of charge between the elements. Sorry. So the first four members are gases, then liquids, then solids, and insoluble in water and soluble in non-polar solvents. So physical properties I told you, and the first four members, that means the methane, ethane, propane, and pentane. They are usually gases, and then they are liquids, and then they are solids. And they are usually insoluble in water and soluble in non-polar solvent. That means where no unequal distribution of charges happening. The important reactions of alkanes are free radical halogenation, combustion reactions, controlled oxidation, isomerism, aromatization, pyrolysis cracking, and reaction with steam. We will be discussing them further. Then halogenation proceeds by a free radical chain mechanism with initiation, propagation, and termination steps. So basically, halogenation here of alkanes is processed by a free radical chain mechanism. That means first free radicals are made, then we are initiating the chain, then the chain propagates, and then the chain terminates, and therefore at the end we are getting an alkane. You can see here in this signature equations, you can see the methane is is getting mixed with Cl2, and then in case of H nu, this is H nu, that is sunlight, we are getting a uh, alkane compound. Okay, these are few examples of the reactions of alkane. Then we have some general features of alkanes. The general formula is CnH2n plus 2. Just a second. Okay, then they have just a second. Okay, this is the general formula of alkanes. They have open chain saturated hydrocarbons. Okay, that means you can usually write your carbons like this. So this is basically C, C, C here, and then you can attach your hydrogens here. Okay, this is how you can write the open chain saturated hydrocarbons. And then carbon is sp3 hybridized, and it has a tetrahedral geometry, and it usually has a typical bond angle of 109.5. I already told you in the previous slide. Then we have nomenclature and isomerism. So how do you name the alkanes? There are certain rules for naming alkanes, and these are very important. So the first step is find the longest carbon chain, and then you have to number the chain, and then name the substituents and write the names alphabetically. Okay. So, for example, first you need to choose the longest chain, number the chain to give lowest locus, show chain isomerism in higher alkanes, and carbon atom may be primary. See, let's say we have this compound, okay, right here, and I have to name this compound now. So, what do? I will write it C. The corners here are C, okay. So, this is C, 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 and C. Okay, then we give the hydrogens. So we have to satisfy the valency of every compound right here. See, this is H, H, H. Okay, so this is basically propane here. Okay, so this is how you can name your chain, and I will show you one more example. Just a second. So whenever you have to name your alkanes, you will always use the suffix "ane." Okay, so whatever your name is, whether it is meth, eth, prop, okay, you will use "ane" at the end so that it is name. Okay, so let's say I have this compound CH3, CH2, and CH3. So according to this thing, first you choose the longest chain. Let me take 1, 2, and 3. So this is the number of my chains. Okay. Then we select the lowest locus. So 3 resembles to what? Sorry, it is the name for probe, right? Meth, eth, probe, you might have studied that. So this is propane here. So what we will do, we will just take this probe, the name, and we will put the suffix "ane" here. So what did we get as a hydrocarbon? It is propane. Okay, this is how you name your alkanes. Okay, just a second, I will give you more examples. Just a second. See, I will take one example with some sort of functional groups there. Okay, see, let me take this example. Okay, I'm taking this example. I am putting chlorine here and I'm taking bromine here. Okay, now these are halogens. Now, how do we name this particular compound? See, we will take the first we will just give the numbers to the chain. Okay, see, we have to name in such a way that the locant. See here, the locant is bromine and chlorine, right? We have to number in such a way that these two locants will get the lowest number. So first I'm taking here as 1, then this as 2, 3, 4, 5, 6, and 7. Okay, this is how I numbered it, so that bromine is getting 1 and chlorine is getting 4. If I had been coming from here, so it would be 1, 2, 3, 4, 5, 6, 7. So bromine would have gotten 7. So we have to name in such a way that all the functional groups are getting the lowest locants. Okay, so now how do we name it? First you take the position. Where is bromine situated? It is situated at 1, so we write 1, then we put a dash. Okay, so 1 dash, and then we have bromine. So you don't write bromine, you write bromo. Okay, so it is 1 bromo, then again a dash. Okay, then what is the locant of chlorine? It is 4, so you write 4 and a dash. Okay, then you have chlorine, so you write chloro. Okay, then again a dash here, like this, and then what you have, the number is 7, so it is 7 here, so it would be hept. And what is it? It is an alkane, so the suffix would be -ene. So this is how you name your alkane. Okay, so this, the name of this compound will be 1 bromo 4 chloro hept ane. Hept, why hept? Because it was 7 number. Okay, is this clear? Give me a thumbs up. You knew how to do it. Give me a thumbs up. Do you want me to take one more example for better clarification? I'm giving you guys one example to try. Okay. Can you do this compound? Just quickly try this compound and then I will show it on my own. How do you name this compound? I will just help you guys with the numbering. Then maybe you can be able to do it. We will number from here. So this is 1, 2, 3, 4, 5, 6, 7, 8, and 9. Did anybody do it? Okay, let me do it then, and then you will see. See, we have two groups here. First one is this right here, and then we have this group right here. Okay, this is our locants. Okay, so or this is our groups that are attached to the hydrocarbon. So first write the group C. We write it alphabetically. So this is methane and this is ethane here. So E comes before M. So we will write ethane first. 6-ethyl, 2-methyl, no name. Who is it? Prince Lion. Yeah, you are correct. Congratulations, you gave the correct answer. Now let me just make everybody else understand. See, this is 6 here. So first we will write 6 right here, and then this is ethyl. So we will write ethyl and then put a dash, and then the second one is present on 2. So we will write 2, and here it is methane. So we don't write methane, we write methyl. So this is methyl. And what is the highest locant? That is 9. 9 is none. So we will write non, and then we have the suffix ane. So this is the name of this particular compound. So this is how you name your compounds. Okay. Then we are moving to the preparation. So the preparation of alkanes is done by hydrogenation of alkenes and alkynes. That means adding of hydrogen to alkanes. Then from alkyl halides by a reduction and Wood's reaction and decarboxylation with soda lye and coal-based electrolytic method. Okay. Then we have the physical properties of alkane. So almost non-polar molecules Alkanes are mostly non-polar molecules. That is, there is no certain kind of uh, unequal distribution of charges. The first four members are gases, the next are liquids, and the higher are solids. They are insoluble in water, but they are soluble in non-polar solvents. The boiling point increases with increase in molar mass. That means if the weight is increasing, the boiling point is also increasing. Then we have chemical reactions or the substitution reaction. So especially alkanes work with halogenation, and then there is combustion that gives CO2 and H2O with heat. Okay, we have studied in 11 that what is combustion reaction. It means burning something in presence of oxygen and it gives carbon dioxide and water with heat. Then we have controlled oxidation, isomerism and aromatization, pyrolysis, cracking, and reaction with steam. Then we have conformations of ethane. So rotation about CC single bond gives conformers. So see, single bond is we are able to rotate the compound because it is single bond. There is no restriction. So this rotation will result into conformers. You might have studied eclipsed and staggered, right? Staggered form is more stable due to lower torsional strain and represented using Sawhorst or Newman's projection. Now, what are eclipsed and staggered uh, these conformers? So these are the two conformers which are there because of the spatial arrangement of atoms formed due to rotation of a single bond, right? Then, in case of structure of ethane, it is sp3 hybridized, and again the bond angle is 109. So, eclipsed conformation is what in eclipse form when hydrogen atom or front carbon come directly in front of hydrogen on the back of the carbon, or there is certain kind of overlap of each other. So, what are the features of this eclipsed form? There is maximum repulsion between the electron clouds, and there is maximum torsional strain. So, this is not very stable as compared to the staggered form. Why? Because there is repulsion, and every compound in chemistry they want that there is no repulsion between them. Okay, it has high energy and is very less stable. Why? Because bonding electrons are very close to each other. Okay, then we have the staggered conformation, right? In staggered conformation, hydrogen atoms are as far apart as possible. Okay, the edge atoms of back carbon appear between edge atom and the front carbon. I will give you a quick representation of. I guess in that way you will visualize it more. See, we are studying about ethane. So just a second. See, let me just zoom it in here. See, first I am drawing the eclipsed, okay? So you will just get a basic idea of what it looks like. So we have two carbon in case of ethane, right? So first hydrogen will be like this, and the second will be like this, and then one will be, see, the wedge representation is for the representation that is coming towards you. Okay, so this hydrogen is coming towards you, means up from the paper. So this hydrogen is towards you, and then this dashed representation is that is going inside the paper. Okay, so this is one representation, and then again we will have a dashed hydrogen here, and then one hydrogen that is going outside, sorry, inside of the paper. So this is eclipsed representation of ethene. Okay, then we have the staggered representation. So these are the two conformers of ethene. So staggered, again we will have two carbon side here, and then we will have one edge on this side, and here we have a dashed hydrogen and a wedge hydrogen right here, like this and like this. Now, what is the difference? Do you see here the hydrogen atoms are both on one side of the carbon atoms, but here it is a little bit like this. Do you see this? Here it is in this position. That is why we call it as a Sawhorst or Newman projection, because the hydrogens are present on the opposite sides of each other. So this is staggered and eclipsed conformation of ethane. Okay, I hope this is clear. Does anybody have any confusion till now? Okay, let's move forward. Then we have the fundamental nomenclature and isomerism of alkanes. Then we studied the general formula of alkanes is CnH2n plus 2, carbon is sp3 hybridized, a tetrahedral geometry, bond angle is, sorry, what happened? Bond angle is 109.5. There is either carbon-carbon bonds or carbon-hydrogen bonds, and they are sigma bonds because they are single bonds. And then we have nomenclature. I told you how do you do the nomenclature? You choose the longest carbon, you put the locants there, and then you name according to the compounds that are attached. Example 3-ethyl, 2,2-dimethyl pentane. Okay, then there is a why boiling point changes. Boiling point increases with the molecular mass because the van der Waals forces increase with size. Now, van der Waals forces are just the intermolecular forces that are present between the molecules, and then branching lower boiling point because the molecule becomes more compact and intermolecular contact decreases. Now, why does boiling point increase? Because the molar mass is increasing because of van der Waals forces. When the size increases of an atom and therefore van der Waals forces are also increasing and therefore boiling point increases. Why? Because the molecule becomes more compact and the intermolecular contact decreases. And then we have isomerism. The first three alkanes have one structure only. Higher members show isomerism. So example C4H10, it will show isomerism. So basically what is isomerism? It means when different compounds have different molecular structure, but they have the same chemical formula. For example, if we talk about this C4H10, this is having that every isomer of this C4H10 will have the same chemical formula, that every C4H10 will have 4 carbons and 10 hydrogens, but their spatial arrangement will differ. How they are present in the space will differ and their molecular geometry will differ. Okay, I will quickly give an example of isomers of C4H10. See, where do I write it? Let me write it down here. Okay, see, we have C4H10. I will be writing down it with a white color. See, we have 1, 2, 3, and 4. Okay, I am not writing down the carbons, sorry, hydrogens. You know कि यहाँ पे hydrogen ही है. So this is basically C4H10. Now I am making an isomer of C4H10. Now you know how these carbons are in single chain, right? Now what if I place 3 carbons here and 1 carbon here? This is also the same structure. This is also having, see, this is also having 3 hydrogens here, 3 here, 1 here, and 3 here. So this is also having 4 carbons and 10 hydrogens. So what is this? This is also C4H10. This is also C4H10. But what is this? This is an isomer of C4H10. Okay. Why? Because the spatial arrangement is different. So this is isomerism. Okay. Then the attached carbon can either be 1 degree, 2 degree, 3 degree, or 4 degree carbon. So what is 1 degree? Which is attached to only one carbon. 2 degree carbon is which is attached to 2 carbons, and similarly 3 and 4 which are attached to 3 and 4 carbons. Okay, then we have you have to always link naming, branching, and isomer count, and then physical property time. Okay, so what is this? You have to first link the naming. Okay, whenever you have to state some kind of physical property trends of any compound, first you do the naming, and then you do the branching, and then you find the links, okay, between the isomers, and then you can simply do the physical property trend, or you can write down what is the similarities between the two isomers. So this is basically the fundamental nomenclature and isomerism of alkenes. Okay. Moving forward, we have the conformations of ethane. I told you the two conformations of ethanes, the staggered and eclipsed. I also show you the diagram. So alkanes show conformational isomerism because rotation about the CC pi bond changes the spatial arrangement of atoms. Now this spatial arrangement is the arrangement in space. Okay, so two extreme conformations are eclipsed and staggered in case of ethane, and they are intermediate forms of skew formations. So staggered conformation is more stable because the repulsion is very less, because their hydrogens are placed in this form, right? I showed you the diagram here. See, here I showed you the diagram, right? So the it are present like this. So therefore the repulsion is very less. But in case of eclipsed, see the bonding hydrogens are placed side to side to each other, right? And therefore there is very less, very greater repulsion as compared to the staggered one. Okay, so staggered is more conformation is more stable because the repulsion between adjacent bond electron cloud is very minimum, and therefore eclipse conformation has maximum torsional strain and therefore very high energy, and therefore it is very unstable. So ethane is usually represented by Sawhorse or Newman projection. So most asked is staggered form is the preferred conformation, and there is energy difference. Eclipsed is form is very small. So rotation is free at any cost. You can rotate the CC bond however you want. There is no restriction to the rotation. Okay. Before moving to the alkenes, just tell me that everything about the alkanes is done. There is no confusion in alkanes. Okay, guys, let's move forward to alkenes. So alkenes, we know what are alkenes. They are the hydrocarbons which contain double bond. Okay. So the general formula for one double bond is CnH2n. The C double bond contains a sigma bond and a one weak pi bond C. When we are talking about double bond, the upper one is always a sigma and the lower bond is always a weaker pi bond. Okay. So each doubly bonded carbon is sp2 hybridized. The region around the double bond is planar. You can see here for the double bond, we have it is sp2 hybridized and the region is planar. So the nomenclature, choose the longest chain carbon containing the double bond C and number from the end nearer the double bond. We will understand the nomenclature in the upcoming slides. So alkanes show chain isomerism, position isomerism, and geometrical isomerism, in which we contain two uh, conformations which are cis and trans. Okay, because rotation around CC is restricted. Now, what is happening in case of single bonds? There was free rotation. You were able to rotate and the bond however you liked, right? Now because the CC, in case of the double bond, the restriction is prohibited. Okay, you cannot you cannot rotate the compound according to your will, because there is the planar uh, representation, and the because of the double bond, simply the rotation is restricted. Some simple examples of alkenes are propene, but1-ene, but2-ene, 2-methylpropanene, and why alkenes are more reactive? Because the pi bond is weaker than the sigma bond, so it acts as a source of mobile electrons and is easily attracted by electrophiles. Electrophiles are the species which love electron. They get attracted to electron and therefore they want to snatch electron from different compounds. So this is why alkenes are basically more reactive as compared to alkenes, because a weaker pi bond is present. So it is a source for the electrons to act as electrophiles. Then we have the preparation and electrophilic addition of alkenes. So the preparation is done by dehydration of alcohols, dehydrogenation of alkyl halides, dehalogenation of vicinal dihalides, and partial reduction of alkynes. The main reactions are addition of H2, X2. X2 is basically halogens, and H2 and H2SO4. And then there is Markovnikov rule. In addition of HX, H2O to an unsymmetrical alkene, H adds to the carbon already bearing more hydrogens. Now, what is Markovnikov's rule? What is this? We will be studying in the further upcoming slides. Decolorization of Br2CCl4 or alkaline KMNO4 is used as a test for unsaturation of alkenes. There is a particular test which is done on alkenes to test whether they are unsaturated or not, and this test is done using alkaline KMNO4. We studied what KMNO4 is, right? Potassium permanganate. It is a purple colored crystalline solid. We studied it in the previous chapter. So high yield additions are when uh, double bond is added with hydrogen, so it yields an alkene. When it is added with halogen, it gives a vicinal dihalide. When it is added with H hydrogen, means hydro halogens, so it gives an haloalkene. And when alkene is added to water, it gives alcohol. So this is basically the reactions you need to remember. Then there is the electrophile attacks the electron-rich pi bond first. The most stable carbocation intermediate usually determines the major product. Now you know what is carbocation. Any species which is having a positive charge on it will be called a carbocation. Okay. Then we have the alkyne structure, acidity, and additions of alkenes. So the general formula we studied, it is CnH2n minus 2. The carbon atoms of, in case of alkenes, I will make you understand the Markovnikov's rule first. Wait, let me write it down here. So in case of Markovnikov's rule, when you are adding an HX, so the hydrogen, let's say, this is my, this is my compound, okay? This is having 2 hydrogens. This is okay, so this is my compound and HX will attack on this compound. Okay, so what will happen? The hydrogen part will go to that carbon which already has many carbons. So let's say this type of this bond we are not having here. This is just an example to make you understand. So this thing, what will happen here? This carbon is having more electrons, hydrogen and hydrogen. This carbon is having more electrons, so hydrogen will move to that carbon which is already having more, the number of more hydrogens, and the halide will go to that carbon which is having the lower number of carbons. Okay, so basically what is Markovnikov's rule? It means that hydrogen goes to the carbon which already has more hydrogen, and the halogen goes to the carbon which is already having fewer hydrogens. Okay, so this is Markovnikov's rule. Then we have alkynes. So the general formula of alkynes is triple bond, CnH2n minus 2. The carbon of atom will have this representation. That means a triple bond. Here also restriction, the rotation is restricted and the carbon is sp hybridized. We studied in case of single bond, the carbon was sp3 hybridized. In case of double bond, it was sp2 hybridized, and in case of triple bond, it is sp hybridized. Okay, the preparation is mainly done from vicinal and germinal halides by dehalogenation, other route in converted unsaturated hydrocarbons, and the terminal alkenes, which are present at the end. That means, let's say this is my chain, and this is called a terminal alkene. That means the alkene that is present at the end of the chain. This will show acidic character because the attached hydrogen is bonded to an sp hybridized carbon and with higher S character. And therefore, see the higher S character. Why? Because this is having 50% S character, right? So this compound will show acidic nature, will show acidic character because it is having a terminal alkene. And in this terminal alkene, the H is sp hybridized, right? And hence terminal alkynes react with sodium or any NH2 to form acetyl ions or salts. So the key addition is done by either H2 or halogens or HX or water. So unsymmetrical additions follow Markovnikov's orientation, which I already told you, that the halogen will go to the carbon with lesser hydrogens. These are the simple examples of some reactions of alkenes. Then we have alkenes key points. Their general formula is CnH2n. They contain one or more double bond. The double bond is one sigma bond and one pi bond, which I already told you. The upper one is sigma and the lower one is pi bond. Okay, and the carbon is sp2 hybridized in case of alkenes. So alkenes show chain and position isomerism. They also show geometrical isomerism like cis and trans. Their restricted rotation around double bond causes cis transforms. Now, what are these cis and trans? I will quickly give an example of cis and trans. See, for example, if I have this compound right here, this is C double bond C. I have chlorine and chlorine here, and then I have hydrogen here. So this will be cis conformation, and this here will be my trans conformation. This is very much similar to the eclipse and staggered. The way staggered used to look. Do you remember staggered? It had a sawhorse uh, like this, right? So in case of trans, it is also looking like the staggered conformation. So this is basically the cis and trans conformation in case of alkenes. This is because the rotation is restricted in case of alkenes. Okay, so they show geometrical isomerism. The formation of cis and trans is what we call as geometrical isomerism. So there is a difference in geometry only. The molecular formula remains same, but uh, there is a dissimilarity in the structure. Okay. Then we have the partial reduction of alkynes give us alkenes, the dehydrogenation of alkyl halides, dehalogenation of vicinal dihalides, and dehydration of alcohols also give us alkenes. And the main reactions contain of electrophilic addition, oxidation, and polymerization. Okay. Then we have alkynes. Their general formula is CnH2 and minus 2. They contain at least one C triple bond. Okay. So carbon is sp hybridized and the geometry is linear. Okay, like in case of CO2. So in case of CO2, the geometry is like this. Okay, so this is a linear structure. That means the angle that is made here is 180 degree. Okay, these are prepared from vicinal or germinal dihalides for dehydrogenation. Okay. Then a quick comparison. Alkenes are saturated and single bond substitution. Alkenes are unsaturated. They have double bond electrophilic addition as their main reaction. And for alkynes, they are unsaturated triple bond addition plus acidic terminal H, which I already told you, because the H at the end of the terminal alkene is sp hybridized and therefore it is most unstable. Okay, then we are moving forward to aromatic hydrocarbons, which is the benzene and aromaticity. Okay, so arenes include benzene and its derivatives such as toluene and naphthalene, right? So aromatic systems are planar, cyclic, and conjugated with delocalized pi electrons. So here we use the Huckel's rule, that is aromatic compounds contain 4n plus 2 pi electrons. That is, if any compound is having 4n plus 2 pi electrons, that according to Huckel's rule, we will consider that compound as aromatic compound. So because of the resonance stabilization, benzene prefers substitution over addition. The ring retains aromatic stability after substitution. So aromatic hydrocarbons are generally non-polar, that is, there is no unfair distribution of charge, and it is immiscible with water. That is, these benzene, toluene, naphthalene, they do not dissolve with water. Okay, they are soluble in organic solvents and often burn with sooty flame. Okay, that means there is a very thick white what is that called? The smoke. Okay, so in case of aromatic hydrocarbons, how we know that they are aromatic or not? We have to look for 4n plus 2 pi electrons. Okay, this is how we will know that a particular compound is aromatic or not. Then we have the examples of aromatic hydrocarbons are benzene, toluene, and naphthalene. They are special class of cyclic hydrocarbons and they are highly stable due to aromaticity. Okay. Now let's say in case of benzene, you know what is aromaticity? It has dancing resonance. That means if this pi bond is moving here, this will move here, and this will move here, and therefore it will get changed to like this. Okay, so this is interchangeable with each other. Okay, this is what we call as a resonance or aromaticity. So how do we determine aromaticity? First, it should be a planar cyclic conjugated system. Then it should have delocalized pi electrons. It should obey Huckel's rule, that is 2n plus 1 pi electrons. And then we have benzene's reactivity. It prefers substitution over addition reaction. Its main type is electrophilic substitution, and ring stability is retained after substitution. Okay. Then we have important reactions of benzene. We have nitration, we have halogenation, sulfonation, Friedel-Crafts reaction. Uh, Somebody is it like white blood screen? What is like white blood screen? Okay, so they see. I guess this was not understood. See, if this pi bond is moving here, this one is moving here. So this is how it moves. So this is what we call as aromaticity. And then there are few reactions of benzene which also consist of Friedel-Crafts acylation. So the substituent position is mono-substituted benzene, which means there is only one substitution. A di-substituted benzene where there is two groups substituted on the benzene. So benzene has literally three positions. This is ortho, meta, and para. Okay, so the substituents that are joining to the benzene can either go on ortho, can go on meta, or can go on para. Okay, these are the only three places where the groups can get joined to uh, the benzene. Here is meta also, this is ortho, and this is para. Okay, so there are two meta, two ortho, and two para. Then hydrocarbons are classified as alkanes, alkynes, and arenes. Alkanes are substitutions. Alkenes and alkynes follow addition reaction. Benzene follows electrophilic substitution. And you need to remember the Huckel's rule, which is 4n plus 2 pi electrons will tell us if a compound is aromatic or not. Okay, we studied this thing. Then we have the benzene reactions and directive influence. Let me change the color. First, we have the main benzene reactions, which is nitration, that is nitrobenzene, which simply means when on the benzene, like this is the benzene ring, if a nitro group, that means an NO2 group, gets attached to the benzene, this is what we call as the nitrobenzene, and this is the nitration process. Then halogenation. If I remove this nitro and replace it with any kind of halogen, then this is the halogenation. Then sulfonation, if I remove this halogen and place a sulfur there, then it is sulfonation. Then Friedel-Crafts alkylation and Friedel-Crafts acylation is also a part of benzene reactions. Then we have electrophilic addition substitution mechanism. First we generate the electrophile, then the electrophile attacks on the benzene and arenium ion, and there is a loss of H plus, restores aromaticity. I will explain this with an example. Just give me a second. I will be writing it down here because I don't have space. See, first of all, we have a benzene, right? And what is doing this? Pi bond is getting up, and this is getting formed into a E plus. Okay, this is an electrophile. Okay, because there are two electrons present, so this is an electrophile. Now, what will happen? This electrophile will get attached here. See, there is an hydrogen. Now this bond is cleared, so there are only two bonds left. So this electrophile will get attached here, okay, because there was a positive charge. And here there will be a positive charge because the electrons went away. Now what will happen? This positive charge will get satisfied this by this pi bond. This pi bond will shift here. So as a result, what happens? Wait. What happens here? See, this pi bond shifted here. Now this will look like this. Now the positive charge will come here. The pi bond is here, pi bond is here. Now again the pi bond will get attracted to this and this pi bond will move here. Okay. In the next step, this benzene will look like this. Now the positive charge will move here. This is here, this is here, and this is H and E as it is. Now again this H will get attracted to this positive charge and it will move here. And what happens in the next step? This is like this and there is E and the H goes here. So this is how the electrophile gets attached to the benzene ring. Okay, then we will have any other kind of compound here. So this is basically the mechanism that is followed in EAS mechanism. So basically what happened here, first the electrophile was generated. Okay, then the electrophile attacked on the para position of the benzene and then the resonance happened. All of these three steps are resonance happening. Okay, resonance happened and therefore H was substituted on the positive charge and therefore we got this compound which we call as the substituted or the proton transfer restoring aromatic benzene. Okay, this is the mechanism of how this happens. So why substitution and not addition? So substitution preserves aromatic ability or aromatic stability. Addition would break the delocalized pi system and is therefore less favored. Okay, so pi system would get breaked if there was addition. Okay, if there was direct addition of the electrophile. So we needed to shift the electrons one by one with the help of resonance. Therefore, this is why we used the substitution mechanism instead of the addition mechanism. Then there is directive influence or mono-substituted benzene. So electron donating groups activate the ring and are generally at ortho or para-directing. Strong electron withdrawing groups deactivate the ring and are generally meta-directing. Halogens are deactivating but still ortho and para-directing because resonance donation. See now what are electron donating and electron withdrawing? This is my benzene and let's say I have some kind of group here named X. If this X has the ability to pull the electron towards itself, we can say that this is electron withdrawing group. That means it is deactivating the ring and it is pulling the electrons towards itself. And usually this electron withdrawing group is present at the meta position. Okay, so meta position is here. It would be usually present here. So if any compound, any electron withdrawing compound is present at the meta position, it will tend to pull the electrons towards itself and therefore it will deactivate the ring. Now, if I have any kind of compound which is present at the para position and it is donating its electron to the benzene ring, therefore it is an electron donating group and it will activate the ring. So usually electron donating groups are either present at ortho or at para position. Okay, so they are usually not meta directing, they are ortho or para directing. So this is the concept of substituted benzene. Then we have the positions to remember. Ortho is at 1 or 2. Let me take an example like this. This is our benzene right here. This is 1, 2, 3, 4, 5, and 6. So ortho is basically 1 or sorry, I just made a mistake. It is like this. The numbering starts from here. 1, 2, 3, 4, 5, and 6. Ortho is basically at 1 and 3. I again messed this up. This is not like this. So I told you where ortho is placed. This is para, this is ortho, this is meta, this is para again, this is meta, and this is ortho. So ortho is at 1 and 3. That means this is 1, this is 3 here. Okay. Meta is at 1 or 3. Okay, you can place 1, 3 and para is at 1, 4. So basically you don't need to remember the numbering, you just need to remember the position that I already showed you right here. Okay, this is the only thing you need to remember in case of the ortho, meta, and para. Just remember this diagram right here. See, this is ortho, meta, para. This is also para, this is ortho, and this is meta. Okay, you just need to remember this diagram in case of uh, the benzene. Okay, use these while predicting products of nitration, halogenation, sulfonation, or Friedel-Crafts reaction in substituted benzene. Okay, now what is Friedel-Crafts reaction? I will just give you a little example. Friedel-Crafts reaction is, there are two types of Friedel-Crafts reaction. One is alkylation and one is acylation. So in case of alkylation, we use RCl in case of in presence of AlCl3. So this is our benzene, and in presence of this, the R will get substituted on the benzene. So this is alkylation. And then we have acylation. In case of acylation, we have an alcohol as our reagent. This is also in presence of AlCl3. So here on the benzene, what will get attached? The R will get attached and also the O will get attached. So this here is alkylation and this is acylation of benzene. Okay, these are the two reactions. Sorry. So benzene is unsaturated yet behaves differently from alkenes because aromaticity strongly stabilizes the ring. So family comparison at a glance, we studied alkanes, we studied alkenes, alkynes, and arenes, right? So the formula for alkanes is CnH2n plus 2, alkenes is CnH2n, alkynes is CnH2n minus 2, and then we have arenes, which means the benzene family. Okay, then we have the single bonds only in case of alkanes. Here we have sp3 geometry. Here the main reaction is substitution, and here we get conformations, which we studied as eclipsed and staggered. Then in case of alkenes, they have at least one double bond. Then they have sp2 at double bond, and their main reaction is electrophilic addition. And they have cis trans isomerism, which I already showed you what is the difference between cis and trans, right? Then in case of alkenes, there is C triple bond. They are sp hybridized. Their main reaction is addition, and they have acidic terminal H. And here we have delocalized pi electron. That means there is aromaticity. Their main reaction is electrophilic and electrophilic substitution reaction. And here we follow Huckel's rule, which is 4n plus 2 pi electrons will tell whether a compound is uh, polar or sorry aromatic or not. Then this is basically a quick revision slide for you. You can use this slide for your revision, and then you can practice questions on it. And this is some topic wise questions. You can again use these questions to just check whether you are having the concepts required or not. So this is basically the end of hydrocarbons chapter. Next, we will be studying the electrophilic substitution in different reactions. And just give me 5 minutes while I'll just load the PDF. So we studied what are hydrocarbons and what are different kind of hydrocarbons. We studied the classification. Now we are going towards the reaction mechanism. Okay. Don't worry, I will be giving you a 1 hour long break at 2 p.m. But first we will complete as much as we can until 2 p.m. Okay. Then you can have a 1 hour break for your lunch time and whatever you want to do. Okay, then we will move with our last topic after our break. That is the periodic properties of periodic table, and that is a very easy chapter. Don't worry about that. And then we will move to the solving portion. Okay, so our session will end around I guess 4 or 5 p.m. Maybe before 5 p.m. So first we will continue with the organic chemistry. Okay. So I will just give you a roadmap of what we are going to study in this chapter here. So first we will have the classification and nomenclature. Then we will have the nature of CS bond. We have preparation methods. We will study what is SN1, SN2, and E2 mechanism. We will study the Grignard and haloarine behavior. We will also study the polyhalogen compounds. Then we will go on to the classification and naming, the physical trends and acidity, the preparation of alcohols, the reactions of OH and CO, phenol ring activation, and ether cleavage plus questions. Then we will go to aldehyde and ketones, where we will study our carbonyl groups, preparation routes, nucleophilic reductions, reduction oxidation test, carboxylic acidity reaction, and final revision and questions. So first we are starting with the haloalkanes and haloarenes. So we know in case of haloalkanes and haloarenes, we studied there are 1 degree, 2 degree, and 3 degree alkyl halides. So what are alkyl halides? Alkyl halides are basically the organic compounds in which one or more hydrogen atom of an alkane are replaced by hydrogen atoms. Okay, so it can be replaced by either fluorine, it can be replaced by bromine, it can be replaced by chlorine, or any other halogen. So basically, alkyl halides or haloalkanes are the organic compounds in which one or more hydrogen atom is replaced uh, by a halogen. Okay, it can be 1 degree, 2 degree, or 3 degree alkyl halide acts on the primary, secondary, and tertiary sp3 carbon. Okay, so if it is 1 degree, it will look something like this. So let's say here it is F. Okay, then again 2 degree will look like, let's say it looks like this, and then 3 degree. Okay, so allylic, the halogen on carbon next to C double bond C. See, if we have any carbon which is here like this, if we have any compound which acts like this, okay, then if there is any halogen next to the C double bond C, that means if we have a chlorine right here, so this will be an allylic compound. Okay, allyl is what, where double bond is followed by a what, is followed by a halogen. Okay, see, here is the double bond carbon, and very next to the double bond carbon is what, a carbon which is having halogen on it. So this is allylic. Okay, so this is allylic. Then vinylic. This means the halogen is directly on sp2 carbon of C double bond C. That means if the carbon was directly present here, it was directly present here, this is vinylic. Okay, there is a difference between allylic and vinylic. So this is vinylic. Then we have aryl halides, in which the halogen is directly on benzene ring. It can be like a nitro group like this. Sorry, it has to be a halogen here. So it would be chlorine right here. Okay, chlorine, bromine, iodine, whatever you want. So gem halides are the same carbon vicinal dihalides adjacent carbons. That means the gem dihalides are having the same carbon. That means they are vicinal dihalides and they have adjacent carbons. Okay. Then we have nomenclature. Halogens have prefixes fluoro, chloro, bromo, and iodo. I gave you an example of that compound, which was 6 bromo, 1 fluoro, let's say diethyl. This is an example of nomenclature where the halogen is written as fluoro, chloro, bromo, or iodo. Okay. Then the number the chain for lowest locants. Again, we will follow the same nomenclature. Then common names still matter, that is chloroform, allyl bromide, benzyl chloride. If there is any compound which is already having a common name, then you do not have to particularly name it using the nomenclature. Then you can use the basic name like formaldehyde, aldehyde. Okay, you just have to use the normal names. Then orthometa para in common benzene naming 1, 2, 1, 3, 1, 4 in IUPAC. Then the nature of CX bond. So it is C is in case of CX bond, because halogens are very electronegative, so they will have a slight negative charge on them, and carbon will have a slight positive charge on them. So this is a polar bond. Okay, all the CX bonds are polar bond. So in case of bond length, this will be your series. Bond length in fluorine is very less because fluorine is very small in size. Then we have CCl, then CBr and Ci, because when we are going down the group, see, this is fluorine, chlorine, bromine, and iodine. When we are going down the group, the size is increasing, right? And therefore the bond length will increase also. So in case of CF, the bond length is very less, and in case of iodine, bond length is very high. Okay, so bond strength, fluorine will have a greater bond strength as compared to the iodine, again because of the size differences. Then haloarenes, in CCl it is shorter than haloalkanes. That means the bond length in case of haloarenes is very shorter as compared to the haloalkanes. Then we have any alkyl group, and iodine generally reacts faster than any alkyl with bromine or chlorine in aliphatic substitution. Okay, so usually iodine is very reactive, so it reacts better than the Br or chlorine. See, these are the examples here. This is allyl bromide. This is benzyl chloride. This is you don't need to remember these. You can also write them in the normal nomenclature, but sometimes you get asked like the common name of acetaldehyde, the common name of formaldehyde, common name of chlorobenzene. Okay, so you need to remember the formulas. Then we have the preparation of haloalkanes and haloarenes. Okay, first of all, we have from alcohols. Okay, we know alcohols are what? It is having any alkyl group and then an OH group. Okay, this is what we call as our alcohols. So if any alcohol mixes with a haloalkane, so it gives RX and water. Okay, let's say we have an example of ROH is mixing with SOCl2. So this R will attack on the Cl and it will give RCl plus SO2 plus HCl. So this is the cleanest method. So what happens here? See, this ROH and this HX. This is having a slight positive charge and this is having slight negative charge. Okay, so this OH will get attracted to this edge because it will form water, right? So what happens? This bond is break down here and this bond breaks here. So what happens? Water and H gets mixed together and they form water, and therefore X and R get mixed together and they form RX. So this is what how we can form an alkane or haloalkane with the from alcohols. Okay. So you understood the formation of haloalkanes with. Then the second is from hydrocarbons. Okay, now we understood what hydrocarbon is. We have, if we have C single bond, we could have C double bond, we can have C triple bond, right? So these are our hydrocarbons. So hydrocarbons, when get mixed with halogens, they can also result into haloalkanes. So first of all, we have if an halogen in presence of H nu, that means sunlight, it gives radical halogenation. For example, what happens? See, if we have C, C, okay, then we have, let's say, Cl and Cl. So radical halogenation means this bond will break and one electron will be given to this and one electron will be given to this. So both the chlorine will get joined here. This is how this is formed, okay, with radical halogenation. Then we have alkene. If alkene gets mixed with hydroalkanes, it gives rise to alkyl halide. Now I told you what alkyl halide is, when one hydrogen is replaced with some halogen. Then we have, in case of alkene, it reacts with Br in presence of CCl4. It gives rise to vicinal dibromine. Now I told you what is vicinal, when the halogen is present just on the double bond. Okay, this is called as a vicinal. Then the second is halogen exchange. Okay, this is Finkelstein reaction. So in case of Finkelstein reaction, we have RCl or RBr, any kind of alkyl halide, and it is mixed with NaI, which is called as dry acetone. It is sodium and iodine's mixture, dry acetone. So it results into Ri, alkyl halide with iodine uh, as the halogen. Okay, so then we have, this is Finkelstein reaction. Then we have Schwarz reaction. In Schwarz reaction, we also have an alkyl halide, but it is added to AgF or SpF3 or COF3. Okay, so it gives rise to RF. It also gives rise to alkyl halides. Then we have reason Finkelstein works well. So if we have to compare between Schwarz reaction and Finkelstein reaction, we will prefer Finkelstein reaction. Why? Because NaCl and NaBr participate in dry acetone, pushing the reaction forward. So they also act as a reagent as well as they act as a catalyst, making the reaction go forward and therefore taking lesser time to accomplish. Okay, that is why we prefer Finkelstein over Schwarz more. Then we have haloarenes. So haloarenes are formed by direct ring halogenation. That means directly on the benzene ring, the halogens are getting attached in presence of FeCl3. See, like I have a benzene ring right here, and I have a chlorine molecule. Okay, so chlorine element. So this hydrogen will leave, and this halogen will attack here. So as a result, what will happen? The ring will have chlorine on it. Okay, so this is direct halogenation, the direct attack of halogens on benzene ring in presence of FeCl3. Okay, this is what we call as the halogenation reaction. Then we have the diazonium route. So okay, so first in to understand what diazonium route is, we will need to understand what diazonium ion is. Okay, so diazonium root, it will have this particular reaction, but diazonium are literally salts. Okay, so diazonium salts are the organic compounds which are containing the diazonium group, and for diazonium group we have uh, N2 positive. Okay, this is our diazonium group. So whenever this kind of group is getting attached to our aryl, okay, or our benzene in presence of CuCl or CuBr, so it gives ArCl or ArBr or whatever the other halogens are. Okay, so example is benzene diazonium chloride, which will be having the formula like C6H5N2 positive and Cl negative. This is an example of benzene diazonium chloride. Okay, this also gives rise to haloarenes. Okay, is this slide clear? Give me a thumbs up. Okay, next we are moving to SN2 reaction. Okay, this is very important. So SN2 reaction is a one-step concentrated reaction. It's just a second. Its rate is KRX and NU minus. I will be making you understand. Here backside attack happens and inversion of configuration also happens. So it is very much best used for first any aryl halide and sorry, any alkyl halide, and then 1 degree, 2 degree, and 3 degree. It is favored by strong nucleophiles and polar aprotic solvent. So basically, what happens in SN2 mechanism? In SN2 mechanism for substitution, a nucleophile or Nu. Okay, here we have a nucleophile which we will call as Nu. It attacks on the aryl halide on the backside of the carbon leaving group, which is the Lg bond. Okay, let me take an example. See, I have a carbon here and I have a leaving group. Okay, leaving group is the one group which will leave the compound. So leaving group, first I will have a wedged hydrogen, sorry, a dashed hydrogen, and then I will have a wedged hydrogen, and then I will have any group R here. Okay, so what will happen? The nucleophile here will come. This is our nucleophile. Okay, and it will attack on the backside of this carbon, that is here backside of the carbon, this nucleophile will attack. Okay, as a result, what will happen here? So The nucleophile will get attached to this. Mm, just a second, just let me just copy this thing here. So as a result, this nucleophile that attacked will get attached here to the carbon, and as a result, what will happen? There will be a partial bond. Okay, this is a temporary bond that is not permanent. So because of this, the hydrogen that is present here will experience more crowding, and therefore it will shift. Okay, it will the leaving group will here leave, and these hydrogens will shift a little bit towards left. So what will happen as a result here? The leaving group will leave and the wedged hydrogen will come here, dashed hydrogen will be here, the group will be here, and nucleophile will make a permanent bond with the carbon here. So this is basically the mechanism of SN2 reaction. Here the backside attack happens. The rate of reaction will depend on both the concentration of the nucleophile and on the concentration of the substrate. That is what we wrote here, both on the nucleophile and on the concentration of the substrate. Okay, another way of saying this is that the reaction is first order in both nucleophile and substrate, and the second order overall. Okay, there is an inversion of configuration. You see, leaving group was on the right side, but here nucleophile got attached on the left side. Okay, is this clear? Give me a thumbs up quickly that the mechanism is clear to all of you. I will also show you what the inversion here means. Let's say I have a compound like this, and Br is joined with a H, and here I have H as dashed. Okay, so when the SN2 reaction will happen, there will be an inversion. So what will happen? This compound will look like this, but the inversion will happen. Okay, the compound will be here, and then the H will be on the dash. So this is what we call as the inversion happening. Okay, so this is our SN2 mechanism. Now we have the SN1 reaction. Okay. So SN2 is basically SN1 is basically a two-step via carbocation reaction. Its rate only will depend on the alkyl halide, and a racemization on chiral center will happen. It is basically favored for 3 degree, more than 2 degree, and more than 1 degree. It is favored by polar protic solvent, and allylic and benzylic halide react fast due to resonance stabilized carbocation. Now I will give you the mechanism of what happens here. So basically, SN1 reaction is a nucleophilic substitution reaction where the rate determining step is unimolecular. Okay, it is a type of organic substitution reaction which stands for substituting nucleophilic unimolecular. The SN1 here stands for unimolecular. That means only one molecule is taking part. The reaction will involve the formation of carbocation intermediate. Okay, let me take an example. Let's say I have a compound like this, and here we have a double bond, and I am doing SN3 in case of CH3OH, and this will result into a compound like OCH3 plus HBr. This is a simple example of SN1 reaction. Now I will make you understand what happens in the reaction mechanism. So for example, let me take an example of this compound right here. Okay, so what happens? This compound will take this bond and it will put into Br. Now what happens here? See, this compound will have, let me write it down like this. This is CH3 here. This is also CH3. This is also CH3. Okay, so as a result, what will happen? This will be my reaction. CH3. Sorry, this is a C here. So Br left, so we will have a Br minus here, and we will have a positive charge on this carbon. This is the first step in our reaction. mechanism. Okay, the halogen is leaving and therefore it is giving a positive charge. Now what is happening in the second step of SN1 reaction mechanism? The carbocation is attacked by the nucleophile. Since water is here used as a solvent on azonian ion intermediate form, so water molecule will come. Now water molecule will come and it will attack on this positive site here. So this water will get attached. Let me write it down here. So this is like this, and here our water will get attached. Okay, now in the third step, what happens? Another water molecule comes and removes this. See, another water molecule comes and takes this hydrogen with them, and therefore what we get is this oxygen and a diazonium ion like this. H3O positive. So this is our SN1 mechanism. So it happened in literally two steps. So first the halide moved and therefore leaving a positive side behind. Then a water from the solvent is attacking on the positive side and therefore getting attached. And then another water molecule is taking the H away with it, therefore forming H3O positive molecule. And here we get the alcohol. Okay, so this is our SN2 reaction mechanism. Then we have our E2 reaction. I will be taking this thing here. I will put it here. Okay. Now we have our E2 mechanism, or this is called as dehydrohalogenation. Okay, so dehydrohalogenation, we will have our compound and it will have uh, sorry, and it will have alcoholic KOH as a reagent in it, and it will give rise to alkene. So here beta elimination takes place. Sedgwick rule is followed, which is more substituted alkane will be the more major product, and higher temperature favors elimination, and 3-degree halides eliminate the most readily. So first, alkyl halide treated with strong base such as alkoxide, that is RO minus. Okay, RO minus or hydroxide, HO minus is used here. Okay, it undergoes elimination. This E stands for elimination here. The rate of these reactions are dependent on the concentration of substrate. Okay, and also on the base. Like in case of SN2, it was depending on the nucleophile and the compound, but here it depends on the base. So let me just quickly tell you what happens here. The reaction requires a CH bond and it will be being removed by anti-planar to C leaving group C. See, I will have, let's say I have a compound like this here, and here Br is joined on the wedge, and I have H here, and this is my any compound D. Okay, now in presence of any E2 mechanism reagent and Na here, this will have a positive charge and this O will have a negative charge. This will result into a compound like this. B will be here and this will be a wedge. So H is on a wedge and Br is on a dash here. And note that the H is removed and not the D, since only H can be anti to the Br. Okay, so the H that was present here is removed. So Br did not get removed. Okay, so the mechanism below, what will this mechanism that I told you here will give you all the observations. Okay, so I will be making you understand it a little bit more. See, this is my another compound and I am taking Br here and I am taking H here as a cis transformation, and this is my H here. So whenever any compound with negative charge, slightly negative charge, it will attack on this H here. Okay, it will take the H with it, and therefore this H will get removed, and this product will result into this compound. Okay, so this is our E2 elimination, where electrophile gets attracted to the negative side, and therefore the hydrogen is removed, resulting into a different compound. Okay, so these are our two basic uh, reactions. Then we are moving forward to Grignard reagent. So Grignard reagent is having Rx plus Mg and dry ether. So this is our Grignard reagent, and it will result into RMgx. So carbon here acts as a nucleophile. It will react with H2O, and therefore alcohol will result in RH. And with HCO, it gives rise to 1 degree alcohol. With aldehyde, it gives rise to 2 degree alcohols. And with ketones, it gives rise to 3 degree alcohols. With carbon dioxide, carboxylic acid after acid workup. So Grignard reagent is basically Mg and dry ether. Then why haloarenes are less reactive? Because aryl CX bond has partial double bond character due to resonance. Okay, carbon is sp2 hybridized, so bond is shorter and stronger. Now I told you what is hybridization, sp2 hybridized, what does it mean? Okay, so um, phenylcation is unstable. SN1 is not feasible here. We studied how SN1 mechanism works, right? But that SN1 reaction is not feasible in case of haloarenes. So electron rich repels nucleophile. The nucleophile which was supposed to attack on the carbon is now electron rich, and the compound is electron rich, and therefore it repels a nucleophile. Only strong withdrawing group at ortho or para position activates the SNAR. Okay, so this is substitution reaction in aryl halides. Then we have polyhalogen compounds. So polyhalogen compounds, they have CHCl2 as their solvent, and CHCl3 solvent stored with ethanol or phosphine risk. Okay, phosgene risk. And they can also have CHI3 as antiseptic iodoform, DDT and CFC chlorofluorocarbons. They are important environmental concerns. Because of them, the environment is getting deteriorated a lot, and therefore measures need to be taken in order to reduce them. Also remember, haloarenes undergo EAS and are orthopara directing through deactivating the ring. Okay. Next we have our unit 6. In this unit, we will be learning about alcohols, phenols, and ethers. So the key idea here is OH group. So the OH group controls acidity and hydrogen bonding in alcohols, phenols, while ethers are less reactive and mainly undergo CO bond cleavage under drastic conditions. Now, what are ethers? What are alcohols? What are phenols? I will be just giving you a little bit of idea. So alcohol, I told you, any aryl group which is having in ROH group is an alcohol, right? This is our alcohol, and alcohols are compound in which hydroxyl group, that is OH group, is attached to an alkyl group. Okay, then we have these alcohols can be of three types. Okay, it can be 1 degree alcohol, it can be 2 degree alcohol, it can be 3 degree alcohol. Okay, so this was our alcohol, and then we will have our phenol. Phenol is basically the benzene with an OH group. Okay, this is our phenol. Benzene having OH group on it is our phenol, and then esters are basically used in perfumes, and then we have different kind of preparation of phenols we will study in the next slide. So alcohols can be mono, di, tri, polyhydric, or 1, 2, 3 degree alcohol depending on the carbon bearing oxygen. So just a second. So this 1 degree primary alcohol, 2 degree secondary alcohol, and the 3 degree tertiary alcohol, if the OH is attached to carbon connecting only one carbon, then it is a 1 degree alcohol. See, like I have an example, CH3, CH2, OH. Okay, this is a 1 degree alcohol because the OH is connected to only one carbon. Then we have a 2 degree alcohol. See, if I have CH3, CH, OH, and CH3. Here, the OH group is attached to two carbons and therefore it is a 2-degree secondary alcohol. And similarly, if it is attached to three carbons, then we have a tertiary alcohol. So phenols are OH directed at aromatic ring, while as ethers are ROR dash symmetrical or unsymmetrical. Okay. So alcohols can be named as alkanol, diol, or triol. Phenol is accepted IUPAC name. So the name for benzene with an OH group is phenol and it is universally acceptable. So ethers are alkoxy-alkanes. Example, you can see methoxyethane or you can see ethane 1O2 diol. And then we have physical trends. That means hydrogen bonding raises the boiling point of alcohols and phenols. So hydrogen bonding, do you know what is hydrogen bonding? See, if we have a water molecule, this is having a slightly positive charge and a slightly negative charge. There is another water molecule like this. This H having a positive charge is getting attracted to this, and therefore there is a bond formation between the two molecules. This is called as hydrogen bonding. There is a slight bond formation between this. This is called as hydrogen bonding. So it raises the boiling point of alcohols and phenols. Alcohols and phenols have higher boiling point than ethers of similar mass. Lower alcohols are water soluble, that means they can easily be dissolved in water, and solubility falls as alkyl chain grows. That means the greater the mass of the alcohol, then difficult it is to dissolve into water. Then we have ethers have lower boiling point but can uh, but uh, but hydrogen bond with water, so lower ethers are somewhat soluble. So because of the hydrogen bonding, ethers are a little bit soluble. Sorry. Then we have how can we prepare alcohols, phenols, and ethers. First of all, alcohols can be prepared from alkenes. Okay, so it is acid catalyzed hydration or hydroboration oxidation. Now, what are these two? I will just take a simple example of acid catalyzed hydration. Just a second. See, in case of acid catalyzed hydration, let me take an example here. See, if we have a benzene like this, and I am taking water and I am taking the acid as H2SO4. So this will result into a compound which is an alcohol. This will have an OH here and this. This is our acid catalyzed hydration. And then we have hydroboration oxidation. In case of hydroboration oxidation, I can give you a simple example of, see, let's say I have an alkene right here and I am adding borane to it. This BH3 here is borane and I am adding hydrogen peroxide to it, H2O2. So this will result into this double bond will break and oxygen and hydrogen will be added. Sorry, this is H only here. Okay, this will also result into in alcohol. Okay, so this is acid boration oxidation. Then we have from carbonyl compounds. That means if we add aldehyde and add an H to the aldehyde, we can give rise to 1-degree alcohol. And from ketones, we can make 2-degree alcohols. And from acids or ether, we can make 1-degree alcohol in the presence of LiAlH4. From Grignard reagent plus carbonyl, also alcohols can be given after hydrolysis. That means if any carbonyl is attracted with a Grignard reagent and then hydrolysis is performed, then it can result into an alcohol. Then phenols can be made from haloarenes and NaOH, from benzene sulfonic acids plus fused NaOH, from diazonium salts. I told you what diazonium is. It is N2 plus and Cl minus, right? From cumene, phenol plus acetone. Okay. Then we have ethers. They can be prepared from dehydration of alcohols, that means removal of water from alcohols, and by Williamson synthesis, that is R-X and RONA will give rise to an ether. Okay, best with 1 degree alkyl halide because reaction is SN2. So ethers are best prepared from SN2 mechanisms, and therefore they are also used in many perfume industries and different. Okay. A small example of ether is like I can tell you like this. This is a small example of ether. Okay. Then we have the reactions of alcohols and phenols. So first of all, alcohols will have acidity with active metals. That means they readily act as acids with active metals. Like if we have an alcohol with sodium, so it will give rise to RONA plus H2. We can determine the degree of alcohols using Lucas test. So 3 degree is an intermediate cloudiness. That means in literally few seconds you can get a smoke, a white smoke. So 2 degree alcohols will result in 5 minutes. That means they will give a little bit of smoke in 5 minutes. And 1 degree, they will have no cloudiness at room temperature. So in case of dehydration, this is the trend that follows alcohols. And for oxidation, 1 degree alcohol can be oxidized using aldehyde and acid. 2 degree alcohol can be oxidized using ketones. And 3 degree alcohol resist mild oxidation. Then we have the acidity of phenols. So phenols are more acidic than alcohols because phenoxide ion is resonance stabilized. Now we know in phenol there is resonance, and therefore they are more stable as compared to the alcohols, right? So the phenols are more acidic than alcohol because they are having resonance in them. So electron withdrawing group increases acidity and electron donating group decreases the acidity in case of phenols. Phenols react with NaOH and ordinary alcohols do not. So this is basically a specialty of phenol, that it is able to react with NaOH, while as different alcohols cannot react. Okay. Then we are having phenol and ring reactions. So OH activates the ring and directs orthopara. So the important reactions in case of phenol is bromination, Colby reaction, Raymer-Tamer, which is the salicylic aldehyde, which gives rise to salicylic aldehyde. Colby reaction will give salicylic acid, and bromination will give 2,4,6 tribromophenol. And FeCl3 test gives violet color. So if we are testing phenol with FeCl3, if it gives violet color, that means the compound that exists is a phenol. Then we have the ethers and final trends of chapter 7. That is ether properties. They are weakly polar. That means they have CO bond. Then boiling points are closer to alkanes than alcohols. So let's say if the boiling point of alcohols is 20 degrees Celsius. I'm just taking an example. So it is very much closer. So it will have almost 15 degrees Celsius closer to alkanes than solids. Okay. So lower ethers are somewhat soluble in water. The alcohols which are having lower alkyl halide in them or alkene groups in them will be somewhat soluble in water, because oxygen can have H bond with water. H bond here refers to the hydrogen bonding. Okay. So much lower boiling point than isomeric alcohols due to no intermolecular hydrogen bonding between ether molecules. So there is not internal hydrogen bonding, and because of this they are having very lower boiling point. Then if we are adding ether to HI or HBr, this will give rise to alkyl halides. Dialkyl ethers can give two alkyl halides, and alkyl aryl ethers cleave at alkyl O bond, giving phenol and alkyl halide. You just need to remember these in case of quick question solving. Then the reactivity of HX is HI, HBr, and HCl. Then we have a quick order. The acidity of phenol is greater than acidity of alcohol. Hydrogen bonding will raise the boiling point, and Williamson works best with 1 degree alkyl halides. And phenol activates the ring at orthopara. Ether cleavage needs strong HX and heat. That means a strong halogen alkyl halide is required, and very much heat is required in order to cleavage the ether. Then we have aldehyde, ketones, and carboxylic acids. So the key idea here is the carbon is electrophilic. That means it will have uh, a slight love for electrophiles. Okay, so aldehyde and ketones undergo nucleophilic addition, while carboxylic acids show acidity and acyl substitution type reactions. Okay, so first of all, we will have the basic naming. So aldehydes are basically named as alkenyl. Okay, that is minus e. Sorry, this is not minus. This is the suffix. That is, either we will take an e or we will take an al. But this is more preferred because most of the books will use aldehyde as al only. Okay, then we have ketones, which is alkenone. Okay, so we will use a suffix of on here, and then carboxylic acid like alkanoic acid, and in case of carboxylic acid, the suffix we have is oic acid. Okay, then ring aldehyde can be called as carbaldehyde. Examples are ethanol, propanol, and benzoic acid. This is an aldehyde, this is a ketone, and this is a carboxylic acid. Moving forward, we have the carbonyl group. So carbonyl carbon is sp2 hybridized, and it has a trigonal planar. Now, how does trigonal planar look like? It is looking like a pyramid shape, like this. Okay, so it is having a bond angle of 120 degree. Okay, here C double bond O is strongly polarized. Now what is polarized? That means unequal charge distribution is happening, and it is strongly polarized. That means C will have a strong delta positive, whereas oxygen will have a strong delta negative charge. Okay, so carbon is electrophilic here and oxygen is nucleophilic. That means basic site. So aldehyde and ketones are more polar as compared to ethers. Then we have the reactivity order. So aldehydes are generally more reactive than ketones in nucleophilic addition because they have less steric hindrance and low positive I effect. Now steric hindrance is what that means: the repulsion between the bond pair and lone pair. Okay, so if there is a less steric hindrance as compared to uh, less steric hindrance in the molecule, then they are generally more reactive than ketones. And a lower I effect. There is a particular series for I effect that you need to know in order to know which kind of aldehyde is having lower and which kind of aldehyde is having positive I effect. Then we have the aromatic aldehydes like benzaldehyde are less reactive than simple aliphatic aldehyde due to resonance. Now, this is a very important concept here. For this, you will need to know what are aliphatic aldehydes. See, I will just take an example. So, aliphatic aldehydes have the general formula of RCHO. Okay, these are having the general. Uh, did anybody raise hand? So, aliphatic aldehydes are organic compounds containing the aldehyde as their functional groups. Okay, so they have a basic general formula of RCHO. Okay, so aliphatic means open chain compounds basically, and they are not aromatic. Aliphatic basically means open chain compounds are present, and the aldehyde is having a CHO group in them. Okay, so this is basically the reactivity order. Then we have how do we prepare aldehyde and ketones. First of all, we have common routes. Okay, so first, if we take 1 degree alcohol and give rise to an aldehyde, that is PCC preferred. So 1 degree alcohol will give rise to aldehyde in case of pyridinium chlorochromate. So PCC here is standing for pyridinium chlorochromate. Is that it is a mild oxidizing agent which is used in organic chemistry. Then 2 degree alcohol will give rise to a ketone. So dehydrogenation over heated copper and silver also works. Ozonolysis of alkenes can give aldehydes or ketones. Okay, so ozonolysis is also a simple reaction. I will take an example of ozonolysis. See, I will tell you how ozonolysis of alkenes can give aldehydes or ketones. Okay, see, first of all, we have alkenes right here. Okay, this is a basic alkene. And what will I do? I will add O3 molecule to it. Okay, it will give rise to an azonide. Azonide looks something like this. Okay, this is my azonide. And then when I add zinc and water to it, this will give rise to my ketone. Sorry, this will give rise to my aldehyde like this. Okay, this is aldehyde. And again, it can also give rise to ketones. This is how ozonolysis gives rise to aldehyde and ketones. Then hydrogenation of ethene can also give acetaldehyde, and hydrogenation of other alkenes can also give ketones. Okay. Then we have aldehydes. Aldehydes can be prepared by Rosenmund reaction, in which we use RCOCl and we add PDBaSO4, and therefore we get a aldehyde in it. Then we have Stephan or diol H from nitriles. This reaction is also very important, and this also gives rise to aldehydes. Then we have Itard reaction from toluene derivatives, Getterman-Koch reaction, in which benzene is added to CO and HCl in presence of AlCl3, and it gives rise to benzaldehyde. I will give you an example of uh, diol H, where I will write it down here. So it gives rise, let's say, I have an ether. Okay, this is an ether here, and I am doing what? I am adding diol H to it. So diol H will give rise to aldehyde. Okay, this is a basic reaction of diol H. It gives rise to aldehyde used from nitriles. Then we have ketones. Ketones can be derived from acyl chloride and dialkyl cadmium. It gives acyl chloride plus dialkyl cadmium will also result into ketone. So basically, its a reaction looks something like this. So we have let me write it down like this, COCl, and we have an alkyl cadmium that is like this, R2CD. Okay, and it will give rise to what? It will give rise to ketones. Okay, will give rise to ketone. So this is the basic formula. Then we have the nitrile plus Grignard reagent, and then hydrolysis will also give ketones. Then Friedel-Crafts acylation, that means benzene plus ROCl in presence of AlCl3 will give rise to aryl ketone. So this is basically how we prepare different kind of alcohols, aldehydes, and ketones. Then we have nucleophilic addition and reduction and oxidation. So first we will take nucleophilic addition reaction. It happens in HCN with cyanohydrin. Okay, NaHSO3 is a bisulfite addition compound. Grignard reagent is also used for alcohols after hydrolysis. In case of alcohols, we use hemiacetal or acetal, and in NH2OH or hydrazine or semicarbodiazide, we use condensation derivatives. Now I will tell you the mechanism of nucleophilic addition. Let's say we have a compound like this. Okay. And what is happening? A nucleophile is coming here and it is attacking on the site. So in the next step, what is happening? The nucleophile is getting attached to the compound. So this double bond which was present here, because of the nucleophilic addition, this double bond is unstable and it will move to the carbon. And then what happens? An H plus ion gets attracted to this to this negative side here. And what happens? This results into an compound like this. Okay, so this is how nucleophilic addition works. So nucleophile attacks on the ketone or aldehyde, and therefore as a result what happens, the H side is getting attracted to the negative side, and therefore it gets resulted into this compound. Then we have reduction. NaBH4 using LiAlH4, it gives rise to aldehyde and 1 degree carbon, and ketone in presence of this reagent will give rise to 2 degree alcohol. Then we also have Clemenson's reaction, which is zinc Hg over HCl gives rise to CH2. Okay, so it gives rise to ethane. And then Wolff-Kishner reaction, which is NH2NH2 KOH, and heat, it will also give rise to CH2. These are the basic two reactions which you need to remember for your exam point of view. Then we have aldehydes, sorry, oxidation test. Aldehydes oxidize easily to acids. That means if you want to oxidize aldehydes, you can use any simple acid. It needs not to be uh, a strong acid. Okay, then we have ketones. Ketones resist mild oxidation, that means they need a very strong acid to oxidize them. Then toluene gives a silver mirror. Okay, and Fehling, in case of Fehling's test, red brown Cu2O is used for aliphatic aldehydes. Okay, so if you want to check aliphatic aldehydes, you have to use Fehling test, which is the use of red brown Cu2O. And then iodoform, in which we use CH3CO, CH3COH, and it gives yellow CHI3. So if you want to check the iodine presence in a compound, you have to use iodoform reaction. Then we have the preparation of carboxylic acids. So it is prepared from 1 degree alcohol aldehyde, from alkyl benzene oxidation, and aromatic acid. From nitriles, it is also obtained by using amides and hydrolysis. Grignard reagent with CO2 is also used, and then hydronium ion is used, and it also results into an acid. So hydrolysis of acyl halide is also used, and hydride and ester also gives acids. Then we have acidity. So carboxylic acids are stronger acids than alcohols. Again, if you have to use a stronger acid in some sort of reaction, so it's better that you use carboxylic acid as compared to alcohols or phenols, because carboxylate ion is resonance stabilized. Okay, so electron withdrawing group increase acidity, and electron donating group decrease the acidity, and direct attachment of sp2 carbon will increase the acidity. Then we have the major reactions, that is anhydride formation and esterification, acid plus alcohol. So anhydride formation is done by esterification, in which we use acid and alcohol. So let's say acid is used with PCl5 over SoCl2. And then we have acyl chloride. So acid plus NH3, ammonium salt, and amide on heating. Okay, so you use acid and then add ammonia to it, and then you get an ammonium salt and amide, and then when you heat you get amide. Okay, so LiAlH4 over dibonene will reduce 1 degree alcohol, and dicarboxylation or Kolbe's electrolysis over HVZ reaction. So these are some questions that you can ask yourself, that why aldehydes are generally more reactive than ketones in nucleophilic addition. You have to write two methods for preparation of aldehydes and for ketones. What happens when aldehyde ketones react with HCN and Grignard reagent? Okay. And then you have to differentiate between Clemenson's and Wolff-Kishner reduction. In Clemenson, we use Zn Hg over HCl. Right? How to do tolerance, what are the carboxylic acids stronger than acids, state the conditions and products. Okay, so this is how you can do. So we are doing a basic quick revision. So haloalkanes are polar, they are CX bond, ready substitution and elimination. Okay, haloarenes are stronger aryl CX, they are less reactive in SN and SN2 inversion, and SN1 gives result to racemization. Then the main reactions are Finkelstein, Schwartz, Grignard, Sandmeyer's, and must known as named reactions. Then hydrogen bonding controls the boiling point and solubility. Phenol is more acidic than alcohol, and alcohols oxidation plus dehydration, and phenols gives ring activation, Kolbe and Raymer-Tamer reaction, ethers give Williamson synthesis, and HIR-PR cleavage. Then in Unit 8, we studied about carbonyl carbons. They are electrophilic. Aldehyde is basically more reactive than ketones. And toluene, valine, and iodine are three key tests which are used to identify the carbonyl compounds. And then carboxylic acids, they are resonance stabilized acids. They are all known esterification, decarboxylation, HVZ, and named reductions. Okay. So basically, we are done with all the named reactions. So do you have any confusion till now? Okay, so we are already done with three of our chapters. Now only one chapter is left, and then we will move to our solving part. So I am giving you a 1 hour break. I will see you guys at 3 p.m. Okay, so I will start again at 3 p.m. We will be starting with the periodic properties of periodic table, and then we will move to the solving part. Okay, thank you for being here with me. We already finished with um, the three chapters of ours, periodic table, hydrocarbons, and the reaction mechanism. Now it's our last topic for this marathon session. After the completion of this chapter, we will move on to the solving portion where we will see some PYQs. Okay, so moving on with this chapter. In this chapter, we will be studying about historical development, the modern periodic table, blocks, periodic trends, okay, reactivity, and then we will see Cossel-Lewis and octet rule, ionic covalent bond, VACPR theory, hybridization, um, MO theory, and edge bonding. Okay. So first we have the classification of elements. So why classify elements? What is the need of classification of elements? Okay. So historical development had triads, which was given by octaves. Okay. So the periodic table organizes a very large number of elements into patterns, families, and periodic trends. Now we are all familiar with what periodic table is, right? It is just a table that was given to us by few scientists, which is basically a table in which elements are classified using periods and groups, right? The chapter moves from early classification attempts to modern periodic law based on atomic number. It connects position in the table with electronic configuration, block classification, and chemical behavior. So periods correspond to principal quantum number, and groups collect elements with similar valence shell configuration. So all the elements which have the similar electronic configuration and similar valence shell configuration, they will be present in one single group, and the principal quantum number similarities will be considered as periods. Then periodic trends will explain size, metallic and bond tendencies, and reactivity. So first we have the historic development of periodic table. So first of all, we will study Dobereiner triads. So triads grouped three chemically similar elements. The middle element showed properties roughly intermediate between the other two. So it had a triad of three elements. Okay, the three elements, the middle element was said to have the atomic mass of the average of the other two masses. So if this was A, B, and this was C, so C was said to have the average atomic mass of A plus B upon 2. Okay, the average atomic mass. So this was Dobereiner's triads, where he arranged the elements in triads. Okay. Then came the Newland's law. So the law of octaves, every eighth element showed similarity when arranged by atomic mass. It worked mainly up to calcium. Okay, so Newland gave the law of octaves, which is also called the musical law of periodic table. Sorry. So what happened in law of octaves? It was that we have that musical instrument of eight rags, that is sare ga ma pa, and then we are moving back to the sa, right? So like the musical notes, we also have the law of octaves, which showed that every eighth element showed the similarity with the first element, and this law only worked up to calcium, that is atomic number 20 only. After calcium, this was not applicable. Then, after Newland's law of octaves, there came the modern periodic law, which was given by Mendeleev. So Mendeleev arranged elements by their atomic mass, but placed similar properties in the same group. Okay, so the elements which were having similar properties, let's say similar reactivity properties, similar compounding properties, all of they were kept in a similar group. He left gaps for undiscovered elements and predicted their properties successfully. So what happened at the time of Mendeleev? Let's say few elements were not discovered. So let's say that this was a group that he was working upon, and this has, let's say, 5 elements. So this element was found, this was found, and this element was not yet discovered. So he left space for this group and kept moving on with the other elements. So later on, when the elements were discovered, they were placed in their respective positions. So this is how Mendeleev's law was versatile and how he was able to give the best law possible. Then came the Moseley's law, which showed that atomic number and not atomic mass is the correct basis for classification of the elements. This led to the modern periodic law, which is today known as the periodic properties are the property, chemical and physical properties of periodic table are periodic properties of their atomic number, okay, atomic weights and not masses. Then we have the modern periodic law and the long form periodic table. So modern periodic law, the physical and chemical properties of elements are periodic functions of their atomic numbers. Now we know in your maths you might have studied what periodic functions are. Okay, they have a little bit of periodicity. That means after a certain interval of time they will repeat. Okay, like in mathematics you might have studied your sine curve, like which is like this somehow. So after a certain interval of time, the sine curve is repeating itself. Okay, so let's say this is the time period t, and after t, this is repeating itself. So this is a periodic function. So similarly, in chemistry, we also see this periodic function in case of periodic table, where the elements have the periodic functions of their of their atomic masses. The long form periodic table has 7 periods and 18 groups. So the periodic table that's known to us in today's world, it has 7 periods and 8 groups. Okay, so elements in the same group show similar outer electronic configuration and therefore similar chemistry. So all the elements that are placed in one similar group will have the same kind of general electronic configuration and therefore similar chemistry. So period number corresponds to the highest principal quantum number of the valence shell. And the 14 lanthanides and 14 actinides are shown separately at the bottom for convenience. Okay, so basically there are 4 groups in our periodic table. First one is the S block, which is having groups 1 to 2. Then we have the P block, which is group 13 to 18. Then we have the D block, which is group number 3 to 12, and they are also called as transition elements. And then we have F block, which is also called as lanthanide and actinides, and they are also called as inner transition elements. Okay, they are also called as inner transition elements. Then we have the electronic configuration and block-wise classification. So first we have S block. Its general outer configuration is ns1 to 2. That means in S orbital, you can only either fill 1 electron or max to max 2 electrons. This only has a space for 2 electrons. Okay. In S orbital, you can only fill 2 electrons. So it is highly electropositive metal and includes all alkali and alkaline earth metals. So all the elements that are present in S block, they are electropositive metals and they include alkali and alkaline earth metals. Okay. Then we have P block, which has the general outer configuration of NH2 and NP1 to 6. Okay. So here P orbital can accommodate 6 electrons. So it will look something like this. Okay, it can max to max accommodate 6 electrons. Okay, and then it consists of metals, metalloids, and non-metals, and it also includes noble gases. Noble gases are the elements which are having stable electronic configuration. Then we have the d block elements. So their general outer configuration is n minus 1 d1 to 10. That means in our d orbital we can accommodate max to max 10 electrons. That means, okay, we can accommodate 10 electrons, and ns 0 to 2. Okay, these are also called as transition elements, and they have variable oxidation states, and they also change color due to dd transitions, which we studied in the first chapter of today's marathon session, right? And then we have the last block, which is called as the F block, and its general configuration is n minus 2 F1 to 14. That means F block will have max to max 14 electrons, and n minus 1 d0 to n s2. This is the general electronic configuration of F block. Sometimes a direct question gets asked to you that write down the general electronic configuration of the F block or D block elements. So you should be knowing this. And F block elements consists of lanthanides and actinides. So each period begins with a new principal shell starts filling. Okay, the number of columns in a block equals the maximum electron that subshells can accommodate. So the number of columns that we have in a block will equal the maximum electron that the shells can accommodate. This is why the S block has 2 columns, P block has 6, D has 10, and F has 14. Okay, elements in the same group have related valence shell patterns and hence comparable chemical properties. Then we have periodic trends in atomic properties. So these are the basic trends which you need to remember in case of solving simple questions. So first of all, we have what happens across a period. So atomic radius decreases, ionization enthalpy generally increases, and electron gain enthalpy becomes more negative. Electronegativity rises and metallic character decreases. Now you just have to remember one simple uh, the trend, and therefore you do not have to memorize each and every of it. You just see how you can do it. So across a period, we know period starts from left to right, right? So atomic radius is generally decreasing when we go across a period. So if we take a group, okay, so let's say we have halogen group. Okay, so when you go down a group, your size increases. Okay, so if you go down a group and the size increases, that means going across a period, your size will decrease. Okay, so you just have to remember across a period what happens. The atomic radius decreases, ionization enthalpy increases. Now, what is ionization enthalpy? It is the energy that is required in order to remove the last electron from its valence shell. Okay, we have already studied what these are. Then, down a group, atomic radius increases as shells are added. Okay, as the number of shells are increasing, and therefore atomic radius is also increasing. Then ionization enthalpy generally decreases, because as the size is increasing, the ability of the nucleus to pull the outer electrons towards itself is decreasing, and therefore ionization enthalpy is also decreasing. Therefore, less energy will be required to remove the last electron from its valence shell. Electronegativity falls, metallic character increases, and non-metallic character decreases. And then, two size facts. Cations are smaller than their parent atoms, and anions are larger than their parent atoms. Now, let's consider a small example. Let's say this is a neutral atom. This is a neutral atom. So we know a cation is a positively charged species, while as an anion is a negatively charged species. Now, when does negative charge get accommodated on an electron? That means when it has gained electrons, right? And this means when it has lost some electrons. So we are saying that cations are usually smaller than their parent atoms. Why? Let's say that this electron is getting away. Okay, so the neutral atom will lose one electrons and it will result into a positive charge. So this size will be like this. So is it smaller than the parent atom? Yes. So therefore it is a cation. While as if I say that this neutral atom has the ability to gain an electron, then what will happen? See, if this was the neutral atom and it is gaining one electron, that means it is gaining one electron as an extra shell. So therefore, size is also increasing. So that is why we are saying that cations are smaller than the parent atom, whereas anions are larger than the parent atom. And then we have isoelectronic species which differ in size mainly because of nuclear charge. Then we have important exception. Chlorine has more negative electron gain enthalpy than fluorine because the added electron experiences less repulsion in the larger 3p orbital and compact 2p. Usually 2p has lesser space as compared to the 3p orbital, and therefore chlorine has more negative electron gain enthalpy as compared to the fluorine. Okay. So you just need to revisit this quick memory lane, that is across period size decreases, ionization increases, electronegativity will also increase, and down the group size will increase, ionization energy will decrease, and metallic character will increase. Then we have metallic and non-metallic character and chemical reactivity. So metals dominate the left side of the periodic table. That is, on the left side of the periodic table, you will mostly find metals. And then on the right side of the periodic table, you will mostly find non-metals. Okay, and metalloids lie along the zigzag boundaries. Okay, so you can find metalloids mostly in the middle or in the zigzag boundaries, whereas the others have a situated corner. So metallic character increases down a group and decreases across a period, while as non-metallic character shows the reverse trend. That is, it decreases down a group and increases across a period. So across a period, ionization enthalpy rises and electron gain enthalpy becomes more negative. So reactivity is high at both extremes but lower near the center. Okay, that means metallites usually have lower reactivity. Then alkali metals react by easy electron loss and are strong reducing agents. Alkali metals are present where? They are present in the S block. Okay, so S block, they are strong metals and therefore they have strong reducing character. So halogens react by electron gain and are strong oxidizing agents because they are more towards the non-metallic character, right? So oxides also reflect periodicity. Left side oxides are basic, right side oxides are acidic, and many central oxides are amphoteric or neutral. So amphoteric is something that can act as both basic as well as acidic. Then we have classic oxide contrast. So this is a basic oxide. If we take NaO and put water in it, so we will get NaOH, which is a basic oxide. While as if we take Cl2O7 and put water in it, we will get an acidic oxide. So metallic character is the tendency to lose electrons, while non-metallic character is the tendency to gain or share electrons. Okay. Then we have chemical bonding and the molecular structure. So why atoms combine, how are bonds formed, and why molecules have different shapes, different spatial arrangements, all of this we will be studying here. Okay. So a chemical bond is an attractive force that holds atom or ions together in a chemical species. Okay, whether it is a compound, it is a molecule, bond is something, an attractive force that can hold atoms or ions together. Bond formation generally lowers the energy of a system and increases stability. So most of the elements will want to create more and more bonds in order to get stable, in order to complete their octet and become more stable. So that is why bond formation happens. Okay, this chapter develops from simple electron transfer, electron sharing ideas to shape, hybridization, molecular orbital theory, and hydrogen bonding. Then Lewis' approach explains valence and dot structures. VSEPR predicts the shape, valence bond theory explains overlap and hybridization, and molecular orbital theory explains the bonding and anti-bonding orbitals and bond order. So first of all, we have the Cosel's idea. So high electropositive atoms tend to lose electrons and highly electronegative atoms tend to gain electrons. This leads to ionic bonding through electrostatic attraction. So any element which is having an electropositive center will have to lose electrons, and because it is having electropositive charge, and any atom which is having electronegative charge, it is said to gain electrons as compared to Cosel's idea. Then we have Lewis's idea. Atoms can also attain stable configuration by sharing electron pairs. So it is not just because that somebody is having electropositive and somebody is having electronegative, so they are just limited to giving and taking of electrons. We can also share electrons according to the Lewis's idea. Okay, so both of the atoms can benefit from each other. This gives covalent bond and Lewis dot structures. Then we have the octet rule. Atoms combine by transfer or sharing of valence electrons to achieve 8 electrons in the valence shell or duplet for hydrogen-like cases. Okay, so what is happening here? So according to octet rule, if any element is having 8 electrons in its valence shell, then it is considered to be stable. Okay. Then Lewis's symbol shows that valence electrons around the element symbol. NaCl illustrates electron transfer. That means Na, if we are giving electron transfer, that is Na will lose one electron and that one electron will be gained by chlorine. Okay. Then Na positive and Cl negative is stabilized by attraction. Okay. And Cl2 illustrates covalent bonding. One electron pair is shared between two chlorine atoms. A single bond, one shared pair, a double bond is equal to two pairs, and a triple bond is equal to three shared pairs. Now understand what is happening here. We have our NaCl compound, okay? And Na is having positive charge, whereas Cl is having negative charge. But what really happened here? The Na lost one electron, and when we lose electron, we put a positive sign here. Now this electron was gained by this chlorine. So this gave rise to chlorine negative. And because positive and negative charges attract each other, and therefore they are in the one compound. Then we have the Lewis structure steps. Now, how do you draw Lewis structures? You have to count the valence electrons. You have to draw the skeletal structure. You have to add single bonds. You have to complete octets on outer atoms. You have to use multiple bonds if needed. And at last, you will check the total electrons. Now, these Lewis structures, what they do, they take electrons as dots, okay? And the dots are arranged around a central metal atom. So this central metal atom is then placed in the middle and the others are made to satisfy the octet. Okay. For example, let's say I am having, where do I make it? Let me do it here. So, let's say I am having NO3. Okay. I have to draw its structure. So first of all, I will take the less electronegative atom in the middle. So here I will take nitrogen as my middle atom. And then I will just place oxygens, okay? But this yet is not electron dot structure. So now I will just place the electrons as dots around the atoms. So we know the oxygen will have 6 electrons in the outer shell. So I am just drawing the electrons as dots, okay? And then I will satisfy the n's valency, therefore I will satisfy it by giving n a double bond. And therefore here only 2 electrons will remain, 2 electron pairs will remain on the oxygen. And this is your Lewis dot structure of NO3. Okay, this is how you make it. Let's take another example, simple example of CO2. Okay, so I'm taking the non-electronegative element as the middle element. Okay, and now I will just place the other elements like this. Now just put the electrons. We know this has 6 outer electrons, right? And carbon has 4 electrons. Right now we have to make the bonds. So what I am doing, I'm just taking one electron from here, putting this one electron here and making a bond. Okay. Now again I'm taking one electron from here, putting it here and making one bond. Now is the valency of the carbon satisfied? No, it is not satisfied. So again I will be taking these two uh, electrons here, placing them here and joining them as a bond. Okay. Again these two electrons, placing them here and joining them. Now carbon's valency is satisfied, oxygen's valency is satisfied, and this oxygen's valency is also satisfied. So this is the Lewis dot structure of your carbon dioxide. Okay, so this is the Lewis dot structure. You can also, if you want to draw the structure more neatly, you can also draw it like this. You can show two lone pairs like this. Okay, so this is our Lewis dot structure. Then we have the formal charge. Formal charge, you just need to remember the formula for the formal charge, which is valence electrons minus the lone pair electrons minus half bonding electrons. So it's the lowest energy. Lewis structure usually has the smallest formal charges. Okay. Then we have the resonance link. Some molecules like O3 cannot be represented accurately by one structure only, so they need a resonance hybrid structure. Okay. Now, what are resonance hybrid structures? When some compounds or molecules, just a second. When some molecules cannot be represented by one single structure, so we use hybrid structure. For example, we have CO3 like this. So we just put a dotted line here. So this represents a hybrid structure. So the pi bond can be anywhere. It can be here, here, here. It can be anywhere. So we don't know the particular position of the pi bond. So we just make a hybrid bond. Okay. So exceptions to the octet rule are incomplete octet. That means few of the elements, even after pairing, their octet remains incomplete, like BH2 and BF3. And odd electron molecules like NO and NO2, and expanded octet, okay, PF5 and SF6. Some either shrink their octet because they are not able to accommodate like more than 3 or 4 electrons, and therefore they cannot take 8 electrons in their valence shell, but some are able to accommodate more than 8 electrons in their valence shell. So this is an exception to the octet rule. The octet rule does not explain all noble gas compounds, molecular shape, or relative stability of the molecules. And formal charge helps compare alternative structures, but it does not mean that the real charges are fully localized on atoms. Then we have ionic bond versus the covalent bond. Ionic bonds are formed by complete transfer of electrons. That means, let's say this is my compound A, and this is my compound B, and it has one electron here, and this has one electron here. If this electron is completely transferred and given to this, so that here now it will not have this, and the electron will move here. So this is called as ionic bond, where the complete transfer of electrons take place. Okay, it is common between electropositive metals and electronegative non-metals. The stability depends strongly on the lattice enthalpy, that is how strong the lattice is and how much energy is required to break the lattice. Ionic solids are 3D lattices of cations and anions. And example, NaCl, MgO, and CaF2 are the example of the elements which are having ionic bond. Then we have the covalent bond. Here the sharing of electron pairs happen, and this can be single, double, or triple. Okay. So shared pairs may be equal or unequal. Best first representation is the Lewis structure, example Cl2. See, if we have Cl and Cl here, the equal sharing of electrons is taking place. This electron is shared by both of the elements. Okay. So ionic bond is favored when low ionization enthalpy is present, high negative electron gain enthalpy is also present. While as the covalent bond is favored when atoms achieve stability more effectively by sharing the electrons. Then we have bond parameters and resonance. So the bond parameter are four different bond trends, which is first the bond length. So the equilibrium distance between the nuclei of two bonded atoms, higher bond ordering usually means shorter bond length. So if I draw the structure of bond length, see, let's say this is the nucleus of my first atom and this is the nucleus of second atom. So if I divide the nucleus into half, so this distance here will be my bond length. Okay, let's take it as L. This is my bond length. Okay. Then we have bond order. The angle between orbitals containing bond pairs around the central atom, it gives direct shape information. So let's say if we have a compound like this. So this arrangement right here is at certain distance. So this here is called as the bond angle. Then we have the bond enthalpy. So energy required to break 1 mole of bond in gaseous state is called as bond enthalpy. So greater bond enthalpy means stronger bonds. That is quite simple because if you need greater energy to break a bond, that means the bond is very strong, right? Then we have the last parameter, which is bond order. So the number of bonds between two atoms in Lewis description, as bond order rises, bond length falls, and bond enthalpy rises. So the number of bond between two atoms is called as bond order. Resonance is used when one Lewis structure is insufficient to describe the experimentally observed structure accurately. Okay, so resonance is used when Lewis structure is basically failing. So canonical forms keep the position of nuclei the same but differ in electronic arrangement. And the resonance hybrid is more stable than any other canonical structure and often explains equalized bond lengths. For example, in O3, experimentally both O and O bonds are equivalent and intermediate between a single and a double bond. Resonance explains this structure better than one Lewis structure. Then we are moving to BSEPR theory and common molecular shapes. So BSEPR theory assumes that valence shell electron pair repel each other and stay as far apart as possible. So if this is my central atom and these are my bond pairs. So according to VSEPR theory, the bond pairs and the central atom will try to remain as far apart from each other as possible. And the repulsion order is lone pair, lone pair. That means two lone pairs will repel more as compared to the lone pair and bond pair as compared to the bond pair and bond pair. Okay, that means two lone pairs will have the maximum repulsion between them. Okay, the multiple bond is treated as one electron domain for shape reduction. The molecules with no lone pair of the central atom usually adopt ideal geometry more closely than those with the lone pairs. Then we are having some simple shapes, which is AB2. It is having linear shape, 180-degree angle, and its example is BeCl2. It looks like this, BeCl and Cl. Then we have AB3. It has trigonal planar structure, 120-degree angle, and example is BF3. So BF3 looks something like this. It has a triangular structure. You see? It has a triangular structure. Then AB4 is tetrahedral. Its bond angle is 109.5 degree. Example is CH4. So tetrahedral looks like this. Then we have AB5, which is trigonal bipyramidal. There are two bond angles. One is 90 and one is 120. And its example is PCl5. I will quickly show you the diagram of PCl5. So these two bonds are 90 degree and these bonds are 120 degree. Then we have AB6, which is octahedral. It has 90 degree. It has 90 degree. Just a second. Its bond order is 90 degree, and then its example is SF6. Okay, next we have the valence bond theory and hybridization. The BB theory explains covalent bond formation in terms of overlap of atomic orbitals. Hybridization mixes orbitals of similar energy on the same atom to form equivalent hybrid orbitals oriented in shape. So basically, BB theory tells you about how bond formations is happening and how atomic orbitals are overlapping with each other. Okay, this explains the shape and bond angle much better than a simple dot structure picture. So there are different kinds of hybridization. First, we have the sp hybridization. It means there are two hybrids. S and p orbital is mixing with each other. They form linear shape, 180-degree angle. Example: BCl2 and C2H2. Then we have sp2. That means one S and two P are getting involved with each other, and therefore there are three hybrids. It gives rise to trigonal planar geometry, 120-degree angle, and example is again BCl3 and C2H4. Then we have sp3, which means one S and three P's are actually overlapping. Now, what is this three P's? It is actually PX, PY, and PZ. Okay, so it gives rise to tetrahedral shape, 109.5 degree angle, and examples are CH4 and NH3. Then we have sp3d, that means one S, three P's, and one D is mixing. Five hybrids are there. Trigonal planar, trigonal bipyramidal is the shape. Example PCl5, whose diagram we saw in the previous slide. Then we have sp3d2. That means one S, three P's, and two D's are mixing. It that means six hybrids. It gives octahedral shape, and example is SF6. SF6 looks something like this. Then we have the molecular orbital theory and hydrogen bonding. So molecular orbital theory or MO theory, it tells us about the atomic orbitals of comparable energy and proper symmetry. They combine to form molecular orbitals. Now the number of molecular orbitals formed is actually the number of atomic orbitals that have combined. Now the number of atomic orbitals that have combined is basically the number of molecular atoms that will be found. So bonding in molecular orbitals stabilizes the molecule, and anti-bonding molecular orbital destabilizes it. And stability requires more electron in bonding and molecular orbitals than in anti-bonding molecular orbitals. So bond order predicts stability here, length and magnetic behavior of different compounds. Then we have combinational conditions. They are same as nearly same energy, same symmetry about the molecular axis, and maximum possible overlap. So here, what are the conditions? That energy should be same, there should be same symmetry about the molecular axis, and then maximum possible overlap should be happening. Then hydrogen bonding, I already made you understand what hydrogen bonding is. It occurs when H is attached to a highly electronegative atom such as fluorine, oxygen, or nitrogen and interacts with another electronegative atom. This may be intermolecular or intramolecular. It strongly affects boiling point, solubility, and structure. So basically, we are done with this chapter as well. So these are the basic questions that you need to ask yourself in order to check whether you have gotten the concept or not. And then there is a quick revision. That means periodicity is based on atomic number. Same group means same valence shell configuration. We have four blocks in our periodic table, S, P, D, and F. And then across a period, the size will size will decrease, ionization energy will increase, and electronegativity will also increase. So metallic character falls across a period and rises down a group. Then we studied about ionic bonds, which means the complete transfer of electrons. Then we studied about covalent bond, which means the sharing of electrons. Okay, Lewis structures. I told you how to design Lewis structures. VSEPR theory predicts the shape and electron pair repulsion. Hybridization tells us about the geometry, while as the molecular orbital theory tells us about bonding and anti-bonding orbitals. Then high yielding lines are Mendeleev predicted the missing element successfully. Chlorine has more negative electron gain enthalpy than fluorine, and lone pair and lone pair will have greater repulsion as compared to lone pair and bond pair, while as bone pair and bond pair will have the lesser. Okay, so basically we are done with this chapter. Now we will be moving forward to our solving part. So all the theory portion is done. So now I will just share with you the PDF and we will start solving the questions. So just give me 5 minutes while I load the PDF. We have questions starting from here. Okay, from question number 181. So first of all, our question is the pKa of an acid and pKa of a base are 4.28 and 4.27 respectively. The pH of corresponding salt form is. So we have to calculate it. So I will just add a page. So this is our question. So I'll be writing it down here. See, we have our pKa as 4.28 and we have our pKb as 4.27. Okay, so now I'll be solving this. So you know your formula for calculating the pH is equal to 7 plus 1 by 2 pKa minus pKb. Okay, just put the values here. So we have 7 plus 1 by 2 upon 4.28 minus 4.27. Okay, so this comes out here to be 0.01. So this is 15 by 2 actually. So when you multiply it, we are getting 7.005 as our final answer. Okay, so this is the correct option. The D is the correct option for the first question. Then we have the Apollo spacecraft, the fuel cell used was. So fuel cell used in Apollo spacecraft was the hydrogen oxygen fuel cell because it has the reaction of two like 2H2 plus O2 gives H2O. This product produced electricity and water for astronauts, and therefore A is the correct option. Okay. Then moving forward, we have when formaldehyde reacts with which of the following compounds to give eutropropene. So we know this, we have studied an equation which is called as HCOH plus 4NH3. It gives CH2 6N4 plus 6H2O. Right? So according to this, eurotrophine, which is hexamethyl N-nitratramine, it is formed by ammonia. So B is the correct option. Okay. Then we have glucose is oxidized into gluconic acid by Tollens reagent. This can be identified through what? We just studied about Tollens reagent and the Tollens test. So it gives the Silver-Miller test with aldehydes, right? So glucose contains an aldehyde group in open chain compound. Therefore, answer D is the correct answer. That is, it gives the formation of silver mirror. Then we have chloroform on decomposition in the presence of air or light gives hydrogen chloride gas along with poisonous gas having chemical formula. Now we have studied this equation. You might remember, I will write the equation here. It is 2CH Cl3 plus O2 gives 2CO Cl2 plus 2HCl. So the formula of the poisonous gas is COCl2. So C is the correct option. Then we have nitrogenous bases found in, first we have this, which shows the correct order of increasing boiling point. So here we know that when the bond increases. So Janya Kumari, could you show the question again? Which question, bacha? 183. 183. Just a second. This one, the Eurotrophine question. 183. Just a second. I will move. I am moving forward. See, here it is. I will write it down a little neatly. It is N. Sorry. It is N4 plus 6H2. Okay. Okay, moving forward, we have, so I was telling you that which was the correct order of increasing boiling point. We know when the chain mass is increasing and therefore we are getting more increase in boiling point. So D is the correct option because first we have methane, then we have propanol, then we have alcohol. So the mass of the chain is increasing, therefore D is the correct option. Then we have nitrogenous bases found in RNA. RNA contains, we know it contains 4 things. We know thiamine is absent in RNA, right? So RNA has adenine, it has guanine, it has cysteine, and uracil. So which one has it? Cysteine, adenine, guanine, and uracil. So option number D is correct. Okay, we remember it by AGCU, right? So AGCU is what you have to remember in case of RNA. Adenine, guanine, cysteine, and uracil. Then we have question number 188. So haloalkanes react with AgCN to form. Now, see, when haloalkane, that is Rx, when they react with AgCN, they give alkyl isocyanides. Okay. Then we have 32 gram of methanol. Just a second. Okay, so 32 gram of methanol contains as many molecules as contained in. Now, how do you solve this? See, I am solving it right here. So, we know what is the formula of methanol. We know methanol is CH3 and OH. So, in order to calculate the molar mass, we know the carbon has 12. We have 4 hydrogens. We have 4 hydrogens, 1 plus 16, which is equal to 32 grams. So what is, it is 4 actually here. So the molar mass of methanol is 32 grams. So 32 grams is equal to 1 mole. So we need another substance with 1 mole in 32 grams. So you have to check the options here. So first of all is what? We have oxygen gas. So 32 grams of oxygen gas will give 1 mole. Okay, so therefore A is the correct option. Then we have the correct value of wavelength of light having period of 2 into 10 to the power minus 10 seconds. So you calculate, just a second, I think this question has some issues. Let's skip this question for now. I will check this and will report back. Moving on to the next question. So we have among the species, okay, which has the largest size? So this is a question that you guys can tell me, which has the largest size. Like in the chat box, tell me why is C the correct answer. See, in case of Potassium, we have the atomic weight as 90. This has chlorine has 70. Sorry, S2 minus has 16 and Ca2 plus has 20. So the largest size would be what? Minus 2, bacha? Jashwant, minus 2. These are the atomic numbers only. Don't get confused with this. So we know this has lost one electron, this has lost two electrons, this has gained one electron, and this has gained two electrons. So most of the electrons are gained by S minus 2. So this is the correct option. Okay. Tell me 192. So it is O2 minus is what? O2 minus is diamagnetic and having bond order 1. It is paramagnetic and having bond order 1.5, paramagnetic and having bond order 2, or paramagnetic and having bond order 2.5. See, since O2 minus will have one unpaired electron, so it is paramagnetic. So option A cancels out because O2 minus cannot be diamagnetic. It has to be paramagnetic. Then how do we calculate the bond order? See, in case of O2, the bonding electrons are 10 and the non-bonding electrons are 6. So our formula for bond order is N non-bonding minus non-anti-bonding upon 2. So this here is 10 minus 6 by 2 for O2. But we have one extra electron for O2 minus. So non-bonding electron here will be 7. So this would be 10 minus 7 by 2. So this is 3 by 2, which comes out to be 1.5. So B is the correct option. Okay. Okay, next question. The value of Kc for the reaction is, can anybody calculate it? Tell me. I will give you the basic. To calculate Kc, you have to take Kp upon RT. You have been given what is Kp. You have been given what is T. You know what is R. It is 8.82. Can you calculate it quickly? You just have to put in the values. But here you will not take it as 8.82. You will take it as 0.082. Option 4. Okay, yeah, yes, you are correct. Who gave the answer? Sojanya. Sojanya, congratulations. D is the correct option. So Kp is equal to power delta Nr. No, this is Kp. Kp is given to you. You have to calculate the value of Kc for this now. So Kc is given by Kp upon Rt. So here Rt comes approximately as 41.05. So when you put it here, so Kp's value is given as 1.8 into 10 to the power minus 2 and upon is 41.05. So it is almost coming out to be 4.3 into 10 to the power minus 4, which is the option B. Okay. Congratulations, Sojanya. You gave the correct answer. Next question. The conjugate base of NH3 is, you know how conjugate base is formed? Conjugate base is formed by removing H plus. So this is very simple answer. Quickly tell me the answer. You just have to remove a one H from NH3. This is N here. This is not B. Misprint. Yes. Option B is the correct option. See, when you remove one H from NH3, so it becomes NH2 minus plus H plus. Okay. Then we have the spin only magnetic moment M2 plus of ion Z equal to 28. You know what is the formula? N into N plus 2. If the atomic number is 28, that means it's nickel. and we have to find for nickel 2 plus. So quickly tell me what is the Bohr's magnetron here, what is the magnetic moment? For nickel, we have the electronic configuration as 3d8. So for 3d8, we will have two unpaired electrons, right? So for two unpaired electrons, what will be the magnetic moment? Okay, yes. Just one. Congratulations. No. But here, according to again a misprint. Again, congratulations, Jaswant. You are correct. Option C is the correct answer because it cannot be zero. This is a misprint here. Okay, great. Now tell me the IUPAC name of CONH35ClCl2. First of all, you will look for the oxidation state, and then you will see the complex charge, and then you will calculate the name of the ligands, and so you will name it. Okay, here again C is the correct option. Then we have the number of coordinate water in CuSO4.5H2O is. So the number of coordinate water here is 4, right? Because the number of coordinated water, we know the structure, it is CuH2O4 SO. I will write it down here how the structure actually looks like. It is CuH2O4 SO4 डॉट H2O. ठीक है, तो ये आ गया इसका structure. Okay, so here how many molecules are present? 4 molecules are present, so therefore coordinate molecules of water are 4. Then we have on hydrogenation, ethene gives ethane. We already studied this in hydrocarbons. Okay, then we have the Van Hoff factor I in case of dissociation of Al3 is. Now you know the formula, it is Al3, it gives Al3 positive and tri-Cl negative. Okay, so the ion produced is 1 plus 3, which is equal to 4. So Van Hoff factor is equal to 4. Is 4 in the options? Yes. 4 is the correct answer. Then the last question here, the quantity of electricity needed to reduce 1 mole of Cr2O7 2 minus. Again, you have to refer to the equation. So which is Cr2O7 2 minus plus 14H plus 6 electrons gives 2Cr3 positive plus 7H2O. So electrons needed are 6 moles, right? So therefore 6F is the correct answer. Okay, we are done with the first part of the 20 questions. Now we are left with 20 more questions. I am just giving you a 5-minute break and I'll be back. Okay, so we have another 20 questions. We will just quickly do them. Okay, so the first one here is this. The colloidal solution that is commonly used in the treatment of skin disease is colloidal anatomy. No, it's colloidal sulfur. Okay, then we have the second question, which is the general name of the compound formed by reaction between aldehyde and alcohol is when aldehyde and alcohol mix with each other or they react with each other, they are called as acetals. Okay, then which of the following hydride is electron deficient? So electron deficient compounds have fewer electrons than required for normal bonding, right? So you have to check each and every option. So first of all, if we check CH4, the carbon has a complete octet and it is not electron deficient. But in case of B2H6 diborane consists of 3 center and 2 electron bonds. So it is electron deficient. So therefore B is the correct answer. Then in fuel cells, dash are used as catalyst. This is a very important question. It gets asked very much amount of time in your questions. So it is platinum palladium in fuel cells is used as catalysts. Then we have the complex hexaamine platinum IV chloride will give dash number of ions on ionization. So it basically has in a reaction that you need to refer to, which is platinum NH thrice whole 6 times Cl4 will give platinum NH3 6 4 plus 4 chlorine atoms. So the total ions formed are 1 plus 4, which is equal to 5 ions. Okay, so 5 is the correct option. Then we have the test to differentiate between 2-pentanone and 3-pentanone is, we already studied the alcohols, so you tell me what is the answer. So basically to differentiate between the degrees of alcohol, I have told you in the previous sessions that we use iodoform test, okay, to differentiate between degrees of alcohol. So B is the correct option. Moving on to the next question, we have an aqueous solution of alcohol contains 18 gram of water and 414 grams of ethyl alcohol. The mole fraction of water is. So we know how to find the mole fraction. First of all, we are given the 18 grams of water and then we are given 414 grams of ethyl alcohol. So first, the molar mass of volume, the molar mass of water is what? Number of molecules upon total molecules, which is equal to 1. Right, so 1 more, and for ethyl alcohol it is 414 upon 46. So this is comes out to be as 9. So total moles will be 1 plus 9, which is equal to 10. So for mole fraction of water, it would be 1 by 10, which is 0.1. Then we have the IUPAC name of cisplatin is. So cisplatin is having the formula as PP NH thrice 2 Cl2. So this has a name as diamine dichloroplatinum 2. So C is the correct option. Then we have an organic compound with molecular formula C7H8O dissolves in NaOH and gives characteristic color with FeCl3. On treatment with borine, it gives tribromo directive C7H5OBr3. So the compound is. So we know the formula is C7H8 and 0 and it dissolves in NaOH, which means that it has acidic nature. Okay, if it dissolves in NaOH, that means it has acidic nature, and acidic nature is of what? It is of phenol group, right? So if it gives color with FeCl3, that means it is confirming that it is a phenol. FeCl3, that means it is a phenol. So tribromo derivative strongly activates aromatic ring. So possible compounds are either orthocresol, paracresol, or metacresol. So we are eliminating benzyl alcohol. Now, because of bromination behavior, we know it has to be a metacresol. So A is the correct option. Then we have the major product obtained when ethanol is heated with excess of concentrated H2SO4 at 443 Kelvin. We know the reaction is CH3 CH2OH in presence of concentrated H2SO4. It gives CH2 double bond CH2 plus water, right? So the product formed here is ethene. So C is the correct option. Then among the following, the products formed by the reaction of anisole with HI are. We know when anisole is reacted with HI, it gives rise to phenol and iodomethane, right? Then in Kolbe's reaction, the reacting substances are, you have to remember what are the reactants in Kolbe's reaction. I will write down the Kolbe's reaction right here. It is C6 H5O Na plus CO2 under pressure, it gives salicylic acid. Okay, we studied it in the previous lectures, right? Always reaction gives salicylic acid. So therefore, sodium phenate and CCl4 is the correct option. Sorry. Sodium phenate and CO2 is the correct option. Then we have ethanoic acid undergoes Hell-Vollard-Zelinsky reaction, but methanoic acid does not. Why is this? So HVZ reaction requires the presence of an alpha hydrogen atom. Okay, HVZ Hell-Vollard-Zelinsky requires what? It requires alpha hydrogen. And CH3COH, which is the ethanoic acid, it has an alpha hydrogen, while as methanoic acid does not. So what is the correct option? C is the correct, sorry, D is the correct option, that is presence of alpha atom in the ethanoic acid. Then vacant space in body centric cubic is about. This is also a very theoretical part. You have to remember it is 32%. Then 195 question number is, if wavelength of photon is 2.2 into 10 to the power minus 11 meters and Planck's constant is 6.6, since h here is Planck's constant, okay? Then the momentum of the photon is, now we know that wavelength is given as what? It is given as 2.2 into 10 to the power minus 11 meters, and Planck's constant is also given as 6.6 into 10 to the power minus 34 joules per second, right? So the momentum formula is P is equal to H upon lambda. So when you just put the formulas, put the values there, you get 3 into 10 to the power minus 23. So is this an option? Yes. C is the correct option here. Then identify the products A and B in the reaction. Okay. So this is the question number 196, and we have an alkyl halide when it is mixed with AgCN. So we know when alkyl halide is mixed with AgCN, what do we get? We get RNC plus AgX, right? So what is A here? So these two options are cancelling out, and then we have to look for B, which is the reaction with KCN, and Rx when reacted with KCN gives what? It gives RCN plus KX. So what is the correct option? A is the correct option. Then the work done when 2 moles of an ideal gas expands reversibly and isothermal volume from a volume of 1 liter to 10 liter at 300 Kelvin, and R is said to be taken as 0.0083. So we have been given, what is given here, I'll just write down. We have given N as 2 moles. P is given to us as 300 Kelvin. V1 is given as 1 liter. V2 is given as 10 liter. And R is given. So we know the work done, the formula for work done is what? It is nRT log of V2 upon V1. So when you substitute the values, you will get 11.5 kilojoules. So C is the correct option. Then a first order half reaction is completed in 45 minutes. How long does it need 99.9% of the reaction to be completed? Now we know if T half, which is the half life, is 45 minutes. Okay, so for the first order reaction, we know T half is what? It is 0.693 upon K, right? So first you have to find out K. So K is 0.693 upon 45. This is our K, right? So this is coming out to be as 0.0154, right? Then for, where do I write? I'll write it down here. So if 1% remains, so initial condition, which is A naught upon A, is equal to 100 upon 0.1, which is equal to 1000, right? The initial and the final conditions. Now for calculating the T half, I am just putting the formula, which is 2.303 upon k log of a naught upon a. Now you know all of the values. So when you put all of the values in this equation, you will get the answer to be as 7.5 hours. So this is option number D. Then we have for spontaneity of a cell, which one is correct? Also, this is a theoretical concept. So you have to remember for spontaneity of a cell, delta G is always negative. Then solubility of a gas in liquid increases with, again, a theoretical concept. It increases with the increase of pressure and the decrease of temperature. So solubility increases when the pressure increases and it decreases when the temperature decreases. So we are done with all of the 40 questions. Just revisit these questions again for your practice and try to solve them once again without looking at my solutions. Okay, without looking at my solutions. So then it will make your solving habits a little bit more clearer. Okay. Thank you for being with me here today. I hope you enjoyed the session. We completed the major chunk of portion of our syllabus. We also solved 40 questions of different. It was not confined to only what I taught you in this lecture today, right? We studied 4 chapters, which was basically the inorganic and organic. But I also took up questions of physical chemistry so that your understanding builds a little bit. So thank you for being with me here today. I hope you will revisit this lecture and you will benefit from it. Thank you. Goodbye. See you again in the next class.